Ladies and gentlemen, please welcome the conveners of this symposium, Professor Skender Kaciu, from the Faculty of Agriculture and Veterinary at the University Hasan Pristina, from Kosovo, and Professor Gordana Popsimonova, from the Faculty of Agricultural Sciences and Food at the University St. Cyril and Methodius, from Skopje, North Macedonia.
Dear colleagues, respected guests, we wish you a warm welcome to the 8th Southeast European Symposium on Vegetables and Potato under auspices of International Society for Horticulture Sciences, organized by two countries, North Macedonia and Kosovo, which is a very exclusive case. It is a symposium that is being held in the region for more than 2 decades. After a relatively long tradition, this time we meet in slightly different conditions, virtually. Yet another feature that distinguishes it from the rest of symposia. From the early beginning, we decided to welcome you in Ohrid with a copy of Acta Horticulture instead of making the proceedings after symposium. We are very glad that we already have it in our hands. At the end of 2019, during the time of abstract collections, we were pleasantly surprised by the interest expressed by scientists from huge geographic scope, from the United States to Japan. We can very well understood that some of the authors were discouraged to submit the full papers with the uncertainty that was imposed on all of us with the corona outbreak. However, there are 56 titles and more than 150 authors and co-authors that are included in this issue of Acta. We want to thank them all for their perseverance. Thank you.
Thank you, Skender. We also want to express our gratitude to the Secretariat of the International Horticultural Society, to our editors, Professor De Pascale, Professor Kitas, and Professor Gruda, to the FAO Regional Office for Europe and Asia, to our respective institutions, the Faculty of Agricultural Sciences and Food at the University St. Cyril and Methodius from Skopje, and the Faculty of Agriculture and Veterinary at the University of Pristina, Hasan Pristina, and most of all to the Ministry of Agriculture, Forestry and Water Economy of North Macedonia for their unconditional and timely support. Let us now walk you through the technical details. Following this opening session, we will start with the thematic working sessions. Presentations, both oral and posters, are pre-recorded, but the discussions will take place at the end of each session will be in vivo via Zoom. At the end of each session, we will have a short break depending on the length of the discussions, and 1 hour break for lunch. We are planning to finish this first day around 5 p.m. Tomorrow we will start again at 10 o'clock, following the same pattern of presentation and discussions. We expect Professor Leskovar to inform us about the conclusions from the closed meeting of the International Society for Horticultural Sciences, that will take place by the end of the working day, also around 5 p.m. The participants that have expressed interest to follow the FAO workshop on climate-smart agriculture and organic production of vegetables in protected cultivation on 26th of September are already communicated with the respective Zoom links. We hope that we will keep your attention during the symposium, and we wish you all pleasant work.
Dr. Stefania De Pascale is a professor at the Department of Agricultural Sciences in the University of Naples, Federico II, Italy, and chair of the Division on Protected Cultivation and Soilless Culture. She will address the audience on behalf of the International Society for Horticultural Sciences.
Distinguished guests, dear friends and colleagues, ladies and gentlemen, it is a great pleasure to be here to welcome participants at the 8th Southeastern Europe Symposium on Vegetables and Potatoes, virtually held on the beautiful Lake of Ohrid in Macedonia. On behalf of the Division Protected Cultivation and Soilless Culture that I have the pleasure to chair, of the Division Vegetables, Roots and Tubers, chaired by Professor Daniele Escobar, of the Working Group Southeastern Europe Vegetable and Potato Production, chaired by Professor Nazim Gruda, and of the entire International Society of Horticultural Science, chaired by the President Yüksel Tüzel, I would like to thank you all for joining this virtual meeting. A terrible virus, the COVID-19, has put the world on pause. Everybody, every continent grapples with the immediate needs of this public health crisis. We probably only just have seen the tip of the iceberg of the many shifts this pandemic will trigger in terms of the socioeconomic fallouts and so much more. However, as someone once said, the show must go on. Not that this is a show, but I appreciate your effort to be virtually together. This symposium is only one of the several symposia, meetings and conferences organized every year by the international community of horticulture under the aegis of the International Society for Horticultural Science. A special thanks goes out to all our conveners for adapting and responding so quickly during this extraordinary time. Our society would never have been able to transition to online meeting without their efforts. The conveners are the people who make the International Society for Horticultural Science the organization that it is. They organize our symposia and meetings, keep them open and on track, and do the basic work that makes our scientific network possible. The meetings are the heart of the International Society for Horticultural Science, and it's the conveners who keep that heart beating. I am very grateful to all of them. Particularly, I want to express my sincere appreciation to my friend Professor Gordana Popsimonova and to Professor Skender Kashu and to their teams. I know the organizing committee spent many months planning the event, and it is short. I would also like to thank the institutions, the Ministry of Agriculture, Forestry and Water Economy of North Macedonia, and the Food and Agricultural Organization of the United Nations, the sponsors that supported the organization, and the keynote speakers, the secretariat, the scientific committee, and all the people that contribute to this meeting. And of course, I would like to thank you all for your participation. I wish you a fruitful and successful symposium.
On behalf of FAO, we are pleased to announce Mr. Nabil Gangi, FAO Deputy Regional Representative for Europe and Central Asia.
Your Excellency, Mr. Anyarit Hoxha, Honorable Minister of Agriculture, Forestry and Water Economy of North Macedonia, President and representatives of the International Society for Horticulture Science, conveners of the symposium, distinguished colleagues, ladies and gentlemen. On behalf of FAO, I wish to acknowledge the President of the International Society of Horticulture Science and the conveners for inviting FAO to address this important symposium. I would like to express my sincere appreciation to the government of North Macedonia and to the Honorable Minister of Agriculture, Forestry and Water Economy for hosting and organizing the 8th Symposium on Vegetables and Potatoes Production for the Southeastern Europe countries. I bring you greetings from Budapest and appreciation to all the scientists, researchers, farmers, and experts from the region who will share in this forum the results of years of research, study, and experience. Excellencies, ladies and gentlemen, I'm very pleased to note that FAO has valued the close collaboration with the International Society of Horticulture Science in our work in the region as well as globally. Since 2001, the FAO Regional Office for Europe and Central Asia has established the Regional Working Group to facilitate inter-country cooperation among Southeastern European countries with a view to capitalize and exchange know-how and supporting research and development initiatives to strengthen national capacities and upgrade greenhouse technology. The working group has been successfully supporting our joint endeavors in holding activities in the region, including this symposium. In the context of this symposium, FAO accords high priority to the sustainable production of potatoes and vegetables, which contribute to our global mandate of eradication of hunger, malnutrition, and poverty, improving agricultural productivity, as well as sustainable management of natural resources and achievement of the UN Sustainable Development Goals. Potato is the third most important food crop in terms of global consumption, world's most important root and tuber crop worldwide. Indeed, in 2008, the United Nations celebrated the International Year of Potato. Likewise, in 2021, we are celebrating the International Year of Fruits and Vegetables, which focuses on raising awareness on the important role of fruits and vegetables in human nutrition, food security, and health. We recognize that we are faced with global challenges, including the need for increased competitiveness along the chain and value added to the products, transformation towards a sustainable production, supply chain, and consumption, the mitigation of the effects of climate change, the implication of changing lifestyles on human health and well-being, as well as an increased ambition for food safety and security and for the reduction of food loss and waste. The increasing impacts of erratic climatic events and changing climate conditions leading to pest and disease outbreaks and changes in productivity of certain cultivars, all of this impact crop production and food security. Horticultural research and development is critically needed to adequately respond to these real upcoming challenges, to secure the fruit and vegetable production system, and to increase its competitiveness through increased focus on sustainability and reduced food waste. The development and applications of good agricultural practices and technologies that enhance productivity in a sustainable manner could contribute to better management of natural resources, including genetic resources, which are essential for coping with climate change impacts. I am pleased to note that this symposium will share valuable research information, technical knowledge, and practices that have the potential to enhance sustainable productivity, increase resilience and food security in crop production, These focus on the five themes: enhancing soil-related ecosystem services and crop nutrition, including through integrated nutrient management, cultivating a wider range of species and varieties in associations, rotations, and sequences, using quality seeds and planting materials of well-adapted, high-yielding varieties, adopting integrated pest management to reduce impacts of pests and diseases, and finally, most importantly, managing water efficiently. The symposium will be dedicated to FAO regional workshop on climate smart agriculture and organic production of vegetables in protected cultivation. Excellencies, ladies and gentlemen, I would like to conclude that FAO is committed to continue supporting the good work of the ISAHCS and the working group to forge partnerships worldwide with development partners, agricultural research institutions, and key stakeholders to address critical aspects of sustainable potato and vegetable production in our region. I wish you a fruitful discussion and a successful participation at the symposium. Thank you for your kind attention.
One of the hosting institutions is the Faculty of Agricultural Sciences and Food from the University Saints Cyril and Methodius from Skopje, North Macedonia. We present to you the Dean of the Faculty, Professor Dr. Vjekoslav Tanaskovic.
Dear Minister of Agriculture, Forestry and Water Economy, dear Rector, dear FAO representatives, dear organizers, dear participants and guests. It is my great honor and pleasure as a Dean of the Faculty of Agricultural Sciences and Food of St. Cyril and Methodius University in Skopje to open the 8th Southeastern Europe Symposium on Vegetables and Potatoes, organized by the International Society for Horticultural Science, the world-leading independent organization of horticultural scientists. Vegetable production is one of the most important single subsectors, accounting for around 1/3 of the total output value of the agricultural production in our country. However, nowadays, we can witness that the climate change on the one hand and the migration of the population living in the most recognized regions for this production in the country, on the other, have an important impact on the performance of this sector and its competitive edge. Therefore, I believe that this scientific gathering is particularly significant since it provides the opportunity to present novel and fundamental results and also promoting and encouraging research and education in the field of horticultural sciences. In this regard, I would like to emphasize that since 1993, when the faculty initiated the organization of such a symposium in Ohrid, we have strongly supported the organization of all Southeastern Europe symposiums on vegetables and potatoes within ISHS, which, despite their regional character, bring scientists from more than 20 countries around the world. Our faculty is the country-leading scientific and educational institution in the fields of agricultural science and food with a 74-year tradition. It is also leading educational institution in the field of horticultural sciences since it is the only one in the region with an established department for vegetable and flower production, as well as study program in horticulture. This fact also demonstrates our teaching staff strong dedication and will to transfer their knowledge and experience in building quality capacities to work in the area of horticultural sciences. At the end, I would like, on behalf of the Faculty of Agricultural Sciences and Food and in my own behalf, to welcome the organization of the 8th Symposium, which enables in very difficult circumstances nowadays to bring together and to foster the communication among the leading researchers in the area of horticultural sciences. I wish everyone a successful symposium. Thank you very much.
The co-organizer of this event is the University of Pristina, Hasan Pristina, in Pristina, Kosovo. We are glad to welcome the rector of the university, Professor Dr. Nasser Sahiti.
Dear participants of the 8th Southeastern Europe Symposium on Vegetables and Potatoes, representatives of institutions of Kosovo and Northern Macedonia, representatives of International Society of Horticultural Sciences, representatives of VIII, dear Professor Popsimonova and Professor Kaciu. Ladies and gentlemen, on behalf of the University of Pristina, Hasan Pristina, it's a pleasure for me to say a few words on opening of the 8th Southern Eastern Europe Symposium on Vegetables and Potatoes, holding together by University of Pristina, Hasan Pristina, Kosovo, and University of Cyril and Methodist in Skopje, North Macedonia. This scientific symposium brings together the international academic staff, researchers, and students aiming to share their scientific experiences and cooperation in field of food production, respectively vegetables and potatoes. This event provides an opportunity to present research work, exchange information and ideas, as well as discussing trends and challenges in the important field. University of Pristina, Hasan Pristina is the largest public university in Kosovo with the highest scientific and research capacities. UP, including Faculty of Agriculture and Veterinary, have very good and long-term experiences in scientific research and services in the country. The agriculture sector, in particular production of vegetables and potatoes, are important resources in Kosovo as well as important sector for economic development. Professional students and scientific researchers, including the organization of scientific events like this current one in this field is of great interest, since in this way is provided the opportunity to present research results for the benefits of researchers, students, professors, and other interest groups from the private sector. The holding of this symposium, as well as many other activities, as a result of the pandemic situation with COVID-19, is taking place in different circumstances. However, even in this situation, I hope it will be a fruitful event. I once again want to congratulate all of you who contributed for the holding of this symposium and all participants, wishing a lot of success and good health.
Please join me in welcoming the Minister of Agriculture, Forestry and Water Economy of North Macedonia, Mr. Arjanit Hoxha.
Dear participants, dear guests, respected friends, on behalf of the Government of Republic of North Macedonia and the Ministry of Agriculture, Forestry and Water Economy, it is my pleasure to welcome you all on this significant scientific gathering. Vegetable production is the leading sector among all the crops in our country. As a ministry, we are thrilled to support all innovative and creative endeavors that will contribute towards further improvement in the research area. Namely, we are aware that the research and development are essential for the economy and the well-being of our farmers. It is on events like this where the ideas to the future are shared, where results are brought to light and recommendations are given on how to move forward. Climate change is a real threat. As years pass by, we feel that more and more. Unexpected weather conditions, floods, and dry summers and devastating fires. We are already witnessing this in North Macedonia, the region, and all the world. It does not stop at any border and speaks all languages. As a minister and the institution I lead, we are deeply concerned about this issue and value every effort to create better and more sustainable conditions. However, This fight cannot be won only by one ethnicity. We are all in this together. Therefore, in this utmost importance to exchange the regional cooperation and research work on implementation of sustainable and resilient agriculture practices. In this regard, it is my pleasure that together with our colleagues from Kosovo, we are hosting scientists not only from the region, not only from Europe, but also from other continents. With these circumstances, I wish you all pleasant and fruitful work. Thank you.
The first of our keynote speakers is Dr. Yüksel Tuzel, President of ISHS and an ex officio member of the ISHS board. She is a professor at the Department of Horticulture, Ege University, in Izmir, Turkey.
Dear colleagues, I am going to present you recent developments in protected cultivation. My name is Yüksel Tuzel. I am from Ege University, Faculty of Agriculture, Department of Horticulture, Turkey. The co-author of my presentation is my colleague Murat Kaçıra, who is from Biosystems Engineering Department, the University of Arizona, USA. Before my presentation, I would like to thank to the conveners and to organizers for their kind invitation to give me a keynote on protected cultivation. I would like to start a general information on protected cultivation, and then I will present recent trends and developments on greenhouse technology, including greenhouse design and developments, models covering materials, agrivoltaics, automation, and robotics, and also sustainable production technologies, including seedling production, soilless culture systems, vertical farming, certificated production systems, and input use. Also, I will give a very brief information on waste management, and then I will complete my presentation with the conclusion. The world population is expected to reach almost 10 billion by 2050, which would result in an increase of food requirement at least 70%. In order to feed the people and improve food security, enhanced technologies and innovations are required to increase the production with limited resources. In this regard, protected cultivation as an intensive production system could contribute with efficient management practices. Protected cultivation presents alternatives to open field cultivation. Protected cultivation includes different types of structures providing a fully, partially, or modified microclimate around the plants against adverse climatic conditions and extending the cultivation season. Global protected cultivation area is estimated over 5.6 million hectares, and it has increased more than tenfold during the last 2 decades. While very simple structures are adapted in mild winter climatic conditions, high technology structures are used in northern countries where the environmental control is more demanding due to outdoor climate and demand of the market for high quality produce. Greenhouses are permanent structures and provide out-of-season crop production with higher yield and quality. One of the main advantages of production in greenhouses is on resource use efficiency. For instance, crop water requirement in greenhouse production is 20 to 40% lower compared to open field cultivation, and water use efficiency is higher. Greenhouses have expanded from northern areas to other climatic regions, including arid and semi-arid regions. In these regions, the main limiting factors for crop production in greenhouse are high ambient temperatures with low humidity and sometimes high temperatures with high humidity, especially in coastal areas. Typical of these regions during almost all the year, the availability of good quality water for irrigation and cooling has been limited. During the last decade, protected cultivation has moved from simple greenhouse structures to high-tech controlled environment plant production systems in which growing conditions of a plant is optimized. There is an increasing interest to indoor cultivation due to the food security concerns, urbanization, and high energy requirement to condition the greenhouses in extreme climates. Control worldwide has received much attention for extension of growing season and increasing the yield and quality with more emphasis on resource use efficiency. Particularly, heating, cooling, ventilation, and lighting systems are more advanced, both plant-focused and data-centric, to optimize the crop production and help growers to make improved management decisions. Let's have a look to the recent trends and developments on greenhouse technology. The improved greenhouse designs and trends have been due to desire to achieve a resource use efficient system that is energy neutral, uses resources optimally with minimal negative environmental impact with maximum net financial return. In the past decade, greenhouse designs and developments included expansion with large volume and large tall structures, integration of innovative covering materials, and closed and semi-closed greenhouses, progress with photovoltaics integrated greenhouses. Screen houses and insect-proof screens providing an acceptable environment for various crops with much lower capital investment than high-tech greenhouses have expanded in warm regions. In this respect, closed and semi-closed greenhouses were studied, and some semi-closed greenhouses have been used commercially due to their advantage to increase CO2 levels inside the greenhouse, reduced pesticide application, and providing energy and water savings. Dynamic models, including mechanistic and black box models, have been developed to increase the knowledge and to control and optimize the greenhouse systems. Progress was also made in development of tools for better and faster design of structures for protected cultivation. For instance, CFD simulations were used to evaluate greenhouse designs, types, ventilator arrangements, crop effects, insect screens. Regarding covering materials, precise characterization of modifications in light quality induced by greenhouse coverings and other materials are needed. Near-infrared absorbing and reflecting covering materials have been developed and evaluated during the last 2 decades. After the oil embargo in the 1970s, various glazing, plastics-based internal energy screens, and plastic plant distributed heating systems using waste energy and solar hot water were evaluated for their viability, and some were integrated to commercial greenhouse operations. Recently, diffuse glass, capable of diffusing light without affecting light transmission in the greenhouse, were evaluated, and positive effects on plant growth and production were reported. Recent developments in material sciences have brought new possibilities for transparent greenhouse covering. Some of these include liquid crystals, photovoltaics, quantum dots. Agrivoltaics, combining agriculture and photovoltaic electricity production on the same land, is an increasingly researched area as a strategy to increase overall land productivity in an increasingly densely populated world. Various integration approaches with photovoltaics into greenhouse have been studied, such as particularly covering the greenhouse roof using silicon PV and therefore partially shading the crops below. A study conducted in Greece showed that covering the greenhouse with only 6.5% of the roof surface could be enough to meet the electricity needs for the auxiliary processes of a greenhouse evaluated in the study. The use of organic photovoltaics as part of a greenhouse cover has advantages, including being lightweight, flexible, and importantly, their absorption spectra can be tuned to mainly absorb light not needed for crop growth. Other materials are currently being developed whose optical properties can be almost instantaneously changed. Are used for monitoring of the growth and the environment in the greenhouse. Non-contact sensing-based crop health and growth monitoring are desirable for practical and crop-centric environmental control. Soft sensors based on crop energy balance can help improving greenhouse environment. An autonomous computer vision guided plant sensing and monitoring system can help to continuously monitor temporal, morphological, and spectral features of crops, providing timely warnings for crop health, stress, and growth status. Protected cultivation, especially with large-scale commercial operations, requires increased labor input. Costs, the availability of sufficiently skilled labor, health problems of the employees due to heavy and repetitive tasks have been a challenge. Automation and robotics can help address these issues. Furthermore, precision and digital horticulture can support production management and help improve the quantity and the quality of crop production with enhanced resource use efficiency. There is a growing interest to integrate artificial intelligence systems in greenhouse and other controlled environment agriculture systems. However, its use and adaptability are in its infancy. In addition to greenhouse technology, new production strategies and techniques have been introduced and adopted during the last 2 decades to contribute to sustainable food supply. One of the most important ones is seedling production. Daniel is going to touch on this issue in his keynote. However, I would like to give a very brief information on the topic. Production in greenhouses starts with transplantation of seedlings due to the many advantages, and seedling quality affects the success of production. Recent trend is the production of seedlings in the specialized nurseries since the 1990s, which makes the possible of using of special techniques such as grafting in addition to other advantages. Grafting is a technique used at the seedling stage of vegetables in order to improve production and resource efficiency. Grafting has become an efficient tool after the ban of methyl bromide to control against soil-borne pathogens. Also, grafting is already used against many abiotic stresses. Soilless culture systems are used very common during the last 2 decades. The problems, such as increasing population, declining of land per capita, industrialization, climate change, have threatened the horticultural production in soil. Increasing demand for food gives a high opportunity to use soilless culture techniques. Soilless culture is growing plants without soil. Plant roots are either in a growing medium, which is called a substrate culture, in which nutrients are supplied via irrigation by dissolving of fertilizers in appropriate concentrations, or directly in the nutrient solution, which is called water culture. Soilless culture systems are further categorized as open and closed systems. The open systems, where the water and nutrients are supplied, as in conventional soil culture, and the surplus nutrient and water is allowed to run to waste. In closed and semi-closed systems, nutrient solution is recirculated, and thus water and nutrient loss is reduced, and the water and nutrient use efficiency is increased. Closed systems are environmentally friendly since these systems also decrease their impact on the environment. During the last 2 decades, sustainable soilless culture systems, such as closed systems or semi-closed systems, have promoted. Additionally, some systems are integrated, such as bioponics, hydroponics, and organic agriculture, and or aquaponics, hydroponics, and aquaculture, to reduce the environmental impact. With the increase of urbanization, intensified hydroponic systems are increased either in greenhouses or controlled environment conditions. One of the recent trends is vertical farming. Vertical farming is proposed as one of the sustainable facilities addressed to meet the food demand. Vertical farming is composed by stacked growing systems, which uses both vertical and horizontal spaces. Plants are grown under controlled environmental conditions throughout the year, with a higher water and nutrient use efficiency and yield per unit area compared to conventional production. The global vertical farming market size was valued as $2.5 billion in 2018 and is anticipated to expand at a compound annual growth rate of 3% by 2025. The high plant density and year-round production capabilities with indoor vertical agriculture with artificial lighting can also optimize space use, help overcoming challenges associated with costs and availability of agricultural land in urban areas. High demanded and high value crops are suitable due to the increasing preference and market price to offset the cost. Particularly, vegetables and microgreens have high demand and consumer interest because of their high content of compounds with nutraceutical and organoleptic properties. Hydroponic systems are utilized for plant growing, such as aeroponics, NFT systems. One of the important developments during the last 2 decades is the introduction of certification process to the protected cultivation. Food safety and security became a major public concern in the 1990s due to the food contamination by detrimental microorganisms and intensive pesticide use. The numbers and concentrations of pesticides are significantly higher in protected cultivation, resulting in higher residue exceedances. This concern related to risks for human health and environment promoted the development of a set of standards to improve production methods, to provide traceability, to control hazards resulting in certificated products and farms, and to improve supply chain transparency. Such programs are to ensure that the products are produced according to the standards needed. Global gap is one of the most common ones used by the farmers. In 2015, over 100,000 hectare protected cultivation area worldwide was certified against Global GAP standard. In addition, according to the report for the province of Almeria, where the highest density of greenhouses is located in the world, almost 79% of the farmers in the province certify their production under quality systems. More than a third of them also have 2 or more certifications. In 2018, the largest growth for Global GAP integrated farm assurance for fruit and vegetables was recorded in Africa as 46.5% in covered crops, and the area is gradually increasing. Production in greenhouses is the most intensive form, providing a higher yield up to 10 times compared with open field production. Therefore, it requires the use of high amounts of inputs such as energy, water, and agrochemicals. Energy consumption varies according to the climatic conditions in the region. Availability of climate control systems such as heating, cooling, lighting, and the level of microclimate control, greenhouse construction, and size and crops. A study analyzing the energy use and carbon footprint of tomato production in heated multi-tunnel greenhouses in Almeria showed that heating increased the annual productivity, while the energy demand per hectare was 5.4 times higher, resulting in 2.75 times increase in CO2 emission per kilogram. Efforts the last 2 decades have been putting forward on the sustainable management of greenhouse microclimate in order to improve energy use efficiency. In Netherlands, CO2 emissions decreased between the years of 2010-2015 due to energy saving. Water is one of the inputs used in protected cultivation and affect production. According to the World Water Development Report, water use has been increasing by about 1% each year since 1980s, and it is expected to rise 20 to 30% above the current level by 2050. Agriculture is the main user of water and faces increasing water scarcity problems worldwide. Compared with open field production, greenhouse cultivation can alleviate this problem by reducing the water use considerably due to the differences in water consumption based on less water loss through evapotranspiration, irrigation system, production system, plant spaces, crop cycle, and adoption of more efficient techniques. Maintenance of sustainable water use is the key issue in terms of water climate policy. Irrigation programs, either in soil or soilless culture, should be able to supply crop water requirement, which is the total volume of water that a crop needs to maintain maximum rates of crop evapotranspiration. There are different approaches to calculate evapotranspiration, and irrigation scheduling is based on water balance method or soil and or plant sensors. Water use efficiency, which is expressed as the ratio between marketable crop production and total crop irrigation supply, can be increased with the improvement of greenhouse structure, increase of crop cycle length, and recycling of nutrient solution in soilless culture systems. For instance, in a totally closed greenhouse in Naldwijk, 40 to 50% of the water supplied to the crop could be recovered by condensation of water vapor from the greenhouse air. In the case of the use of closed soilless culture systems, decreases of water and nutrient consumption by about 22 and 35% respectively. Some other findings reveal an average nutrient saving of 32-34% in tomato, 48% in rose, and 15% in chrysanthemum production. Water use efficiency could be as high as 66 kg per cubic meter for tomato production in the glasshouse with heating and CO2 enrichment in the Netherlands conditions. Agrochemicals are used during the production to achieve a high yield. And the agrochemical market was worth $243.1 billion worldwide in 2019, and it is expected to increase to almost $300 billion in 2024. The amount of applications is affected by environmental conditions and lack of climate control. Despite the importance of agrochemical use in agriculture, the risks of extensive use of pesticides and fertilizers, in particular nitrogen use, is very well known. In order to prevent any pollution originated from agricultural facilities, developed countries has been established programs and/or directives aiming sustainable use of agrochemical and promoting the use of good agricultural practices. Rising public concern regarding to excessive agrochemical use and consumers' demand for the products free from any residue has resulted in the introduction of biopesticides, biofertilizers, and biostimulants in the last decade, gradually replacing mineral fertilizers and synthetic pesticides. These are nature-identical materials obtained from animals, plants, and living microorganisms. Although biopesticides and biofertilizers have still a small share in the market, it will increase in the coming years. I would like to say a few words about the waste management, since suitable waste management is important to reduce the environmental impact. The amount of solid waste, such as plastics, crop residues, is one of the most important problems in greenhouse horticulture. Therefore, there could be some treatments to improve the waste management. For example, composting of biodegradable matter could reduce the environmental burden by between 40 and 70%. Converting crop and food waste to produce organic fertilizer can help reducing the demand on inorganic fertilizers, improving waste management practices, and using resources wisely in controlled environment food production systems. Considering all the recent developments and trends on protected cultivation, it is concluded that sustainable crop production in greenhouses has become an important issue due to the change in consumer demand and increasing awareness of potential damage to the environment. Any technology and/or technique should aim to reduce the use of agrochemicals and improve the resource use efficiency, especially with energy, water, nutrients. Labor and logistics management is a critical need due to lack of access to farm workers in many regions. Therefore, innovations and further integration of automation and robotics in controlled environment agriculture is a significant need. Outcomes of research with LED lighting will continue to enable unique opportunities to enhance crop yield and quality and help improving the profitability of controlled environment agriculture. Developments and integration of artificial intelligence and more data-centric growing practices in controlled environment horticulture will help growers to improve decision-making and production management. Protected cultivation will play a significant role and continue to contribute to sustainable solutions to feed increasing world populations with nutritious, safer, high yield and quality food using resources more efficiently. Thank you very much for your attention.
We will give the floor now to the second keynote speaker, Professor Daniel Leskovar, Chair of Division Vegetables, Fruit and Tubers. He comes to us from Texas Agricultural and Mechanical Agri-Life Research and Extension Center at Uvalde, USA.
Good morning, everyone. My name is Daniel Leskovar. I'm a professor in horticultural sciences at Texas A&M University. And today I'm going to present a topic related to vegetable transplant quality and stress tolerance through root-to-shoot growth modulation. This work done in collaboration with my PhD student, Quan Chin. Before beginning, I want to really thank the organizers, in particularly convener Professor Gordana Popsimonova, for the kind invitation to be here today to present. In transplant quality, a critical factor that affects morphological and physiological processes in young seedlings is root confinement. And root confinement can have an important consideration in terms of different traits that relates to transplant quality. When we're looking at high quality transplants, we're looking at those plants that are compact, they're not elongated, they have strong stems, they're uniform, they have a balanced root-to-shoot growth. And importantly is that can be acclimated to stress, particularly abiotic stresses, depending on where those plants are going to be transplanted. One aspect that we're interested is in the ability of the plants, of the young seedlings, to compensate for the lost roots that occur during transplanting. In other words, can those seedlings produce fine roots immediately upon transplanting? And that's an important aspect that will be for them to be able to have a better water uptake and nutrient uptake upon transplanting. So ultimately, the goal is to produce plants that will reduce the transplant shock, that they will have a rapid recovery in terms of leaf growth, for example, leaf expansion, and we have higher relative growth rates, both on the root traits like length or surface area, or shoot growth rates, and ultimately produce a plant that we have a beneficial crop productivity and yield. Here on your right, you can see 4 examples of high quality transplants. On the top, lettuce, leeks, artichokes, and watermelons. And you can see on the right the 2 examples of elongated, low quality transplants for a bell pepper and a watermelon plant. There are important factors affecting root and shoot growth and productivity, and those are in relation with the genotype, the crop type or variety type that is being considered, the environmental conditions, that you can see the list here, and then management factors that includes also microbes. There are many of those management factors. For the sake of time, I'm going to describe those that are highlighted here in red boxes, and provide some quick examples on aspects related to root-to-shoot growth modulation. We know that nitrogen is perhaps the most important factor affecting the speed of the seedlings growth in the nursery. So in other words, if you have high level of nitrogen, you will speed up shoot development in relation with the root development. And it has been a lot of research being conducted and published in tomatoes, peppers, and lettuce, whereas low levels of nitrogen were correlated with reduced shoot growth. I want to highlight just one study that we've done a few years back in artichoke transplants, in which we compare low versus a high level of nitrogen on growing transplants and measuring several root traits and shoot traits. And you can see here in the table. Those numbers in blacks indicate percentage promotion effects as compared to the high nitrogen levels, while the numbers in red indicate the promotion effects in the shoot aspects, decreased aspects as compared to the promotion effects in black numbers. So you can see that low level of nitrogen increased root length and surface area and produce shorter and compact plants, while low level of nitrogens produce much less leaf area and shoot length as compared to the high nitrogen levels. And those plants also that we produce with low level of nitrogen were able to tolerate stresses in the field. We have much less wilting as compared to high level of nitrogen transplants upon transplanted under warm temperatures. The PGRs, there's a lot of PGRs that have been tested for trying to grow in transplants and trying to slow down the growth or use these PGRs as a tool to replace low water deficit or low nitrogen levels. And one of them has been ABA. We've done quite a bit of work through the last 10, 15 years. And we have seen some very interesting and positive results on spraying ABA on several crops. In this case, you can see here on the left, applying ABA on artichoke transplants that were exposed to a desiccation period, were able to improve the stress tolerance as compared to those that did not receive ABA. And similar results were found in other species like melons or match melons. ABA also, we have tested those in a variety of crops to try to determine the potential for reducing plant height, either controlling development by applying early on, for example, 3 to 4 weeks before transplanting, or controlling the height at maturity. And you can see here 2 examples of plant height reduction for jalapeno pepper on the left, on the middle left, and then the seedless watermelons, the reduction in plant height. However, despite these beneficial effects, there is difficult in terms of application in the real world, because really this requires very precise application timing, application dosage, and conditions of the seedlings, prior to being sprayed or applied, or also after transplanting. Organic soil amendment has been also an interesting potential tool as a plant biostimulants to improve root and shoot growth of young plants. We have tested the humic substances pre-transplanting and also post-transplanting on a variety of crops, including peppers, tomatoes, watermelon, lettuce, and artichokes. And we have seen clear improvements of root growth as well as shoot growth on these species, that then these improvements were translated in high crop productivity from these 5 crops, with increases as compared to control anywhere from 10% up to 40%, depending on the type of species. And then specifically, we're looking at the root to shoot growth changes. Here we see, for example, changes in leaf biomass and root biomass. You see those two graphs, and then before transplanting and after transplanting. The dotted red line indicates the time of transplanting. And you can see that the increase in the leaf and root biomass, especially after transplanted, was much higher for the humic substances treated seedlings. Those are showing in a solid black line. And then also when we transplant those under drought conditions or heat stress conditions, we in general have seen that stronger transplants perform much better under those conditions as compared to the control. And this example in the first graph in bell peppers, you can see that the same trends occur in tomatoes, lettuce, and watermelons that we're not showing here. Plant biostimulants also involve the use of plant growth promoting microorganisms known as PGPM or PGPR, and Bacillus species have been a group of materials that have been having important promoting effects in species like tomato. You see here in root growth, promoting root growth and promoted shoot growth. Importantly is that there is differences between strains. So selecting for different strains is actually very to consider when we look at the different Bacillus types or even microderma types. Here we can see that microderma is also have the ability to enhance growth with better nutrient uptake, but also some of the literature relates the potential induction of plant resistance by the use of trichoderma species. However, the literature is mixed, and so there are some that incorporate results that relate to promotion, like in the case of the first two publications here, but some others show detrimental or conflicting results. And so really the evidence remains to be seen depending on conditions. Particularly trichoderma has been mentioned that it's more unlikely to increase productivity when there is no stress conditions. As I mentioned for Bacillus, again, the same for trichoderma, it's important that there are different strains. And this is an example where wheat seeds were coated with trichoderma, different strains, and you can see there is the differential responses as compared to the control. Our experience in terms of potential enhancement of plant biostimulants have not really been very positive in general. And on the left, you can see a large study that we did on using trichoderma species as it incorporated in dipping transplants prior to transplanting, or actually incorporating those at transplanting in a watermelon fields, but we have not seen really differences in productivity. The results, the productivity of these, all of the control and trichoderma treated plants were incredibly high, but failed to show additional differences, particularly in conditions that were non-stressful. We're currently conducting a fairly large experiment in which we are comparing organic sources like humic substances together with a compound that the nursery uses. It's called root shield based on trichoderma, also by using a calcium-based treatment, and then comparing the productivity of those seedlings. We've seen initially that the organic source have a much better transplant quality trait as compared to the other treatments, including the trichoderma base. In terms of productivity, we really see minimal differences in any of those treatments, except for the humic substances, a slightly better production as compared to the other treatments or control. Now, a previous work by Kwan, my graduate student, in peppers and watermelons, have shown that humic substances can increase the rhizosphere microbial biomass in the soil when measuring the soil. And you can see here in that table, the red boxes for the AB, which stands for the active bacterial, that the humic substances, or HS, have increased as compared to the control in terms of the rhizosphere. Also, the humic substances significantly increase the soil organic carbon. And interestingly, we have seen in several of the tests that humic substances improve root development, root traits, particularly fine roots. So on the other hand, fine roots are very important, and work done in other horticultural crop like peaches, it has been observed that fine roots actually have a much larger bacterial diversity as compared to medium-sized or large-sized roots. So an interesting hypothesis is whether plants that have the ability to be have a promotion effect of humic substances in fine roots can also harbor a much larger bacterial diversity and subsequently with that increase resource use efficiency like nitrogen uptake or water uptake. That's the question that remains to be tested. In terms of light, as we all know, plants respond through photoreceptors to light conditions, particularly stem elongation. And LED light has been a tremendous tool in the last decade that has been used mostly to modulate growth and productivity, especially in the controlled environment conditions, and including for potential use in seedlings. In this case, I'm going to show a couple of examples, one by Bantis et al., who look at the composition of light, looking at different ratios of red and blue, from anywhere from a ratio of close to 1 to 10, and then using watermelon seedlings and squash seedlings with the idea of producing uniform seedlings for grafting. And you can see that a higher ratio of red to blue light produce better seedling quality with the stem diameter, stem elongation, leaf area, as well as biomass, as compared to low levels or low ratios of red and blue. On the other hand, when we look at the light duration, work done in Korea by Wei et al., especially for growing watermelon, two watermelon grafted varieties under conditions of more or less light in Korea, particularly in autumn or winter where there is much less light. They supplement light and compare 8, 12, and 16 hours. And you can see here clearly that 12 hours or 16 hours of supplemental light cause promotion effects in both shoot growth and root growth significantly as compared to 8 hours of supplemental light. And they recommended actually the use of 12 light instead of 16 hours, because 16 hours also cause some level of stress since they measure certain metabolites, particularly hydrogen peroxide and some other antioxidant enzymes that indicates that this 16 hours may cause a slight stress, so 12 hours will be much more efficient and also less costly due to the number of hours of supplemental light. Grafting is very well known as a tool, as a root power system to increase the growth and productivity of particularly solanaceous crops like tomatoes and also cucurbits like watermelon plants. A study conducted by Lee, my graduate students in my lab, is showing that grafting Scion tomato 1823 or Maxi 4, he clearly saw an improvement in root trait, root length, root surface area, and root dry weight. And these increases were also expressed when those transplants were transplanted under a water deficit as well as heat stress. So this is, again, pretty important in areas that are characterized by these kind of abiotic stresses. In addition, the grafted plants have less stress damage as they show much less electrolyte leakage in the leaves, and also they have a higher photosynthetic rate as well as a higher productivity. So another important consideration in grafting, as many of you know, is the selection of the rootstocks. This can have an important implication in how plants adapt physiologically and morphologically to different stresses. And a work done by a visiting graduate student from Brazil in my lab have tested a commercial scion, tomato scions, grafted on wild-type tomatoes, Solanum pinelliae and Peruvianum, and then compare the physiological measurements and show that, for example, those plants grafted into these two rootstocks have a much better physiological adjustment and express much less water stress when they were subjected to drought stress as compared to well-watered conditions. You can see in the boxes with red compared to the self-grafted plants that the water potential was higher as compared to those, or less negative as compared to the untreated self-grafted plants. So this again indicates the importance of selecting rootstocks, particularly when we're considering these biotic stress conditions. Finally, I want to have a couple of 2 or 3 pictures in terms of real applications. This is an application where when there is combination of more than one growing factor. As you know, growers use a multitude of crop management strategies to increase productivity of their field. So in this case, when combining the application of organic sources like humic substances with grafting, it causes a synergy in the plants that increase productivity and the greenhouse conditions. This is particularly done in the southern Spain, in the Almeria region. On the other hand, here very close to our research center, when growers combine application of organic sources like humic substances with strip tillage, using a cover crop systems and seedless watermelon, they have seen important promotion effects in terms of productivity as compared to the control conditions. And finally, I think some future trends in terms of defining transplant quality for different type of containers will be interested in terms of when you consider new systems like a plant tape developed by the industry, has been implemented in California, particularly for large growers. This system actually produces seedlings that are not in true containers. The taproot is unrestricted. So in a sense, it will have a very nice adjustment and establishment in the open field. And they're using the system through automation, complete automation system. But of course, this would be beneficial for very large growers and will be very difficult to be adopted by small scale farmers where they're more used to the classical containerized transplant systems. So to conclude, just want to define that, as mentioned, there are very attractive tools to modulate root and shoot growth traits that can improve the transplant quality and the abiotic stress adaptation. So we talk about some, plant growth regulators, carbon-based media, spectral light blends, and maybe new biomolecules that can have this promoting effect that can be considered in the near future. I think also with modern breeding, we produce different vegetables, different hybrid types that they may have different capacities for water uptake, nutrient or light use capture, and abiotic stress tolerance. So this will create some new challenges in nursery systems, how to manage those plants, but also will create opportunities to be able to maximize some recipes to be producing plants for those conditions. And I think that also the different type of containerized transplant, like in the plant tape, will require also some definition of the transplant quality traits, because obviously there is some initial modification of the root systems. And so those traits that are in the classical containerized transplant may not hold true in these kind of scenarios. So with that, I just want to also thank members of my past team. You can see here a fairly large group some years back. They have worked in ABA, for example, Dr. Shinsuke Agihara, Sumiliana Goreta, Togo Shinohara. And then more early work, in terms of onions and peppers with different hormones that I didn't mention today, Desiree Dijunou and Andrea Macias, and then work with Yahya Oldman from Jordan in terms of the nitrogen work in artichokes. And then you can see here on the left my current team that are working mostly in organic soil amendments, as well as the grafting and for abiotic stress, particularly heat and drought stress. And of course, thanks to the funding agencies, both private, state, and federal agencies that have been supporting this work. With that, again, I want to thank all of you and the organizers for giving me the opportunity, and I'm looking forward to see you later during the presentations and the Q&A sessions. Thank you.
Dear colleagues, it is a pleasure to present the paper titled as Vegetable Production in North Macedonia, Competitiveness, Trends and Challenges, prepared by myself. I'm Aleksandra Martinovska-Stojčevska, Ruki Jagic and Ivana Janeska-Stamenkovska, all part of the Faculty of Agricultural Sciences and Food at St. Cyril and Methodius University in Skopje. The aim of this contribution is to provide an analysis of the vegetable subsector in North Macedonia and to investigate the trends and patterns in production and trade, all in order to see which are the factors that shape the competitiveness in the last decade and identify some challenges ahead. The vegetable subsector in our country is one of the most important ones. It takes up 1/3 of the agricultural gross product, or up to 40% if we include both vegetables and potatoes. There are many factors that influence the performance of this subsector and the competitive edge. And we see here the competitive edge as the ability to operate successfully, produce and sell products profitably at the right price, quality and quantity. We base this research on secondary data from the statistics and both national and international. And we also conducted a tailor-made survey with 100 primary vegetable growers to get their personal view and perception on the sector. We use a standard statistical method and also the revealed comparative advantage index, which is a metric that helps identify the country's weak and strong export sectors and can be analyzed within the domestic market or for the foreign market. The set of countries that we consider are the countries in the Western Balkans, but also the regional EU countries and the remaining EU countries. Vegetables are produced on around 50,000 hectares in North Macedonia, and the annual production reaches around 900,000 tons. We can see from the graph that this is a relatively stable production, both in terms of area covered and in terms of quantity produced. The production is scattered around the country, but is mostly present in the southeast region, in Skopje region, and in the Pelagonia region, though in terms of quantity produced, the leader is the southeast region. The key crops are tomato, pepper, cabbage, watermelon, and cucumber, which take up around 70% of the production and around 90% in export quantities. Which are the key features of the subsector? We have around 60,000 growers, which are typically very small family farms and have several plots of land that they cultivate, with an average size of the farm being 0.8 hectares. They face many challenges starting from the beginning of the production. We saw through the survey that the choice of cultivars is a big challenge because in order to hedge the risk, they choose to grow many different cultivars, and usually the seedlings are produced on farm. They face some challenges in the production practices, but most evident are the harvesting and post-harvesting practices, which often cause losses and damage quality. The lack of farmers' integration is a big issue, which results into poorly organized buyout, prices which are non-remunerative, and lack of trust of buyers. And last but not least, also which causes issues in contract farming. The trade trends reveal that in North Macedonia over the last decade, the value of vegetable trade is on slow increase. But on the other hand, the volume of vegetable trade has decreased in terms of exports. On the other hand, we can see that there is a very evident increase in imports, both in terms of volume and value, which, although it is still very small compared to the whole trade, its share is increasingly rising over the years. Out of the quantities export of the country, which are around 130,000 tons annually, 80% are exported as fresh and the remainder is processed or exported as frozen. The 5 major crops trends are very are revealing that the export value is slowly decreasing over time, while at the same time the imports we can see that have increased over the last decades almost fivefold. And this is something that raises the alarm. The Western Balkan countries are the major trading partner, especially in terms of imports, while exports are also going to the EU in the region or in the wider European Union region countries. This all led us to calculate the revealed comparative advantage index, which we can see that in North Macedonia has fell substantially from 2.69 in 2019 to 1.91 in 2010. The trend is similar in other countries except for Albania, where we can see that 10 years ago it was a country with low revealed comparative advantage, and now it has the highest index in the Western Balkan countries. The decreasing comparative advantage trend of North Macedonia is also confirmed when analyzed in terms of specialization of the Western Balkan countries in relation to the world trade of vegetables. During the last decade, North Macedonia has lost its vegetable export competitiveness in this regard by around 50%. We can also analyze the relation to individual countries' exports, and this all shows some declining comparative advantage of the vegetable trade and weakening export competitiveness. The biggest decline we can see is evidenced with respect to the Slovenian vegetable exports, with the index equaling 3.47 in 2010 and now falling to 0.67 in 2018. The trend is similar also in Romania, Greece, Bosnia and Herzegovina, while in the other countries in the region and in the EU we can see still persisting to the comparative advantage of our country. So this leads us to the conclusion that the subsector is still very important, but the challenges that are being faced really need immediate attention in order to maintain the competitive edge, which is obviously weakening. We can see rising competition from the neighboring countries, numerous challenges on the production and value chain side, and also changing market structure and growing dominance of large retailers. So what are the remedies? We group them in 5 categories. We see that there is potential for interventions in on-farm practices, starting from choice of inputs, quality of inputs, harvesting and post-harvesting practices, and always how to differentiate from the competitors to have better cost structure, better quality, consistent quality, reach efficiency, and also faster adopt new technologies. Between farm practices are also very important because farms are small. The concentration of supply and joint production planning is very important. And here, the horizontal integration of farmers is very important. Also, the vertical integration is very important, and changes in value chain practices, where, for example, both supply and demand can be coordinated, and special emphasis here should be put on the functioning of the contract farming. The policy needs to support the scaling up of farms through various instruments, for example, land consolidation, and more attention should be paid to the structural and rural development measures, rebalancing from the direct payments to this segment. Last but not least, the advisory, knowledge and innovation transfer is definitely very important and needs to be improved, because this is basically the competitiveness backbone of every sector, including the vegetable sector. Thank you very much for your attention. You have in the last slide our email contacts, and we are all available for further discussion.
Welcome everyone. I would like to present the paper The Influence of Microclimatic Conditions on Hot Pepper Quality Compounds. In changing climate conditions, many stenothermal plant species from warm regions can be successfully grown in Central Europe. Protection of plants against the potential frost can be achieved by direct covering or with a low tunnel covered by plastic film. Nevertheless, the microclimatic conditions under this material with a limited air volume are difficult for plants. Covers that are permeable to air and can shade plants during strong insolation are suitable alternatives. The aim of this study was to compare the effects of a few types of polymeric covers on microclimatic conditions during the initial stage of plant growth and on the fruit quality indicators of hot pepper originating from two continental and tropical climate zones. The experiment was conducted at the experimental station of the University of Agriculture in Kraków, Poland, in humid continental climate. The research was carried out in 2018-2019 on the pepper cultivar Biała Szipka originating from Bulgaria and cultivar bird chili from Thailand and included 4 treatments. The control, no cover, low tunnel with a double layer perforated film, polyethylene net, non-woven polypropylene fabric. Materials and methods. Seeds were sown in mid-April and the plants transplanted in the middle of June. The 50 cm high and 3 meters long tunnels were covered with appropriate covers, which were removed at the beginning of July. Harvesting was carried out in the middle of September. Cultivation was performed in an organic system. The details concern methodic or are described in the paper. It is crucial to notice that average temperature recorded in both years was higher than the one recorded over the last 50 years time span by 2.6 centigrades on average. At the same time, average precipitation level was lower by 12.9 millimeters. It should be noted that in recent years, rainfall was distributed unevenly. The amount of PAR radiation reaching the plants were reduced by the covers. The perforated film had transmitted 81%, the highest in this respect. The net and non-woven fabric transmitted about 15% less. The highest relative air humidity was recorded in the film-covered tunnel, where it was more than twice as high as outside. The reason for this was the considerable better air insulation compared to the other permeable covers. The difference in relation to the outside temperature was on average 10 centigrades, whereas under the net it was warmer only by 2.7 centigrades and under the non-woven fabric by 5.5 centigrades. There were no significant differences in the amount of CO2 under the covers and outside. Due to the presence of plants, there was 1–2% less CO2 under the covers. The soil moisture was higher under all the types of cover. Relative to the soil moisture outside, the smallest difference was recorded under the net, which facilitated rainwater access the best. Short covering, the pepper plants in the initial stage of growth had a rather small influence on their development, phenological stage and fruit quality. It's important to notice that origin of the cultivars had the biggest influence on the ripening and the quality of the fruits. Higher content of dry matter was found in cultivar Biała Szybka in both years. This indicates incomplete ripening of bird chili peppers and suggests earlier sowing and planting in the conditions of the present-day climate in southern Poland. The amounts of soluble sugars in the fruit of the two cultivars also differed significantly. In the cultivar Biała Szybka, their amounts were several times higher. The concentration of vitamin C in both years was significantly bigger in cultivar Biała Szybka. In first year, both cultivars synthesized smaller amounts of vitamin C, but the amounts estimated in cultivar Biała Szybka were on average by 126% higher, whereas in the previous year the difference was 21%. The analysis of these basic components shows that in our experiment their values significantly exceeded the results obtained in Bulgarian conditions. Antioxidant activity in the fruit of Biała Szybka was in both years markedly higher than in bird chili, especially in 2019, which was the result of a lower degree of fruits ripens. There was also a clear difference between the years for the Thai cultivar. Higher concentration of phenolic compounds in 2018 were estimated in bird chili. In the second year of the experiment, the phenol's content was higher in Biała Szybka. The amount of capsaicin in the fruit of cultivar Biała Szybka was in both years greater than in cultivar bird chili. It was only one exception. Notice, please, that the amounts of capsaicin estimated in ripe fruits delivered from Thailand and Bulgaria and analyzed by the same method in 2018 were 3.7 and 0.76 milligrams per 100 grams respectively. Conclusions. Protecting hot pepper plants with low tunnels covered with a perforated polyethylene film, polyethylene net or non-woven polypropylene fabric modified the microclimate in the initial period after planting, but did not affect the condition of plants during the period of intensive growth, nor the fruit ripening time. Fruit quality indicators, dry weight, soluble sugars and vitamin C were at a much higher level in cultivar Biała Szybka, which indicates a better adaptation of this cultivar to the changing climate of southern Poland. The levels of antioxidant activity, phenolic compounds and capsaicin in the pepper cultivars originating from the different climate zones indicate their dependence on the degree of maturity, which could only be fully achieved in cultivar Biała Szybka. High capsaicin content in the fruit can be achieved by selecting appropriate varieties originating from more similar climate zones. Thank you for your attention.
Hello everyone, I'm Yannis Karavidas. I'm a PhD student at the Laboratory of Vegetable Production at the Agricultural University of Athens, and I will present you my study with the title Impact of the Preceding Crop on Soil Nitrogen Availability and Fresh Pod Production in an Organic Crop of Common Bean Grown in Open Field. Nitrogen is a macronutrient required at high amounts by plants to increase yields to sustainable levels. In organic agriculture, nitrogen is one of the key factors limiting productivity, as its supply in the form of an organic fertilizer is unacceptable. Nitrogen supply to organic farming systems is mainly achieved through renewable organic sources such as legumes, used and green manures, animal manures, compost, and crop rotation schemes comprising nitrogen-fixing crops followed by nitrogen-utilizing crops. However, nitrogen from these sources is unavailable to plants immediately after its application. Therefore, in organic crops, the well-timed nitrogen supply is more important than the total amount of nitrogen applied. Taking into account the above background, the main objective of this study is to improve nitrogen supply via alternative renewable organic sources in organic agriculture. To achieve that, we tested the impact of the preceding winter crop on a spring-summer cultivation of common bean in organic farming systems under mild climatic conditions, allowing for winter cultivation. The standard practices during the preceding winter in fields cultivated organically with the common bean are either a left fallow or cultivation of a cold season legume during the winter as green manure crop. In a curious study, in addition to this standard option, the possibility to cultivate organically a cold season vegetable during the winter as a preceding crop to a summer cultivation of common bean was also investigated. The rotation of a winter non-legume vegetable with a spring-summer common bean crop during the same year was tested following also conventional farming practices which served as control. To obtain results that are more credible and test the long-term effects of organic fertilization on organic crops, the crop sequence was repeated over 2 years in the same field. During the winter cultivation period, a 1-head broccoli hybrid was cultivated under conventional and organic farming systems. To apply green manure, a local land race originating from the Greek island Lefkada was used to establish the fava bean crop. All of the above treatments were replicated 8 times. At the end of the winter cultivation period of both experimental years, the plant residues of the above crops were incorporated into the soil. During the subsequent spring-summer cultivation period, a climbing variety of common bean was cultivated. In the plots with treatments of organic broccoli, fallow and fava bean during the winter, organic farming practices were applied in the subsequent common bean crop, while in conventional farming of broccoli, the subsequent common bean crop was treated according to conventional farming practices. At the following slide is represented the total nitrogen fertigation scheme for both experimental years. In organic crops, sym manure was applied as nitrogen source, and the total nitrogen inputs did not exceed the limit of 170 kg nitrogen per hectare. In addition, as a too low soil nitrogen availability during the early vegetative stage may restrict rhizobia nodulation in legume crops, the plots intended for fava bean cultivation were fertilized with sym manure as well. Concerning conventional broccoli, the increased supply of nitrogen during the second compared to the first experimental year was due to the higher fertigation requirements during the second year because of less precipitation during the cropping period. To assess nitrogen availability in soil samples were collected at critical developmental stages of the common bean crop, and nitrate nitrogen were determined through cauberized cadmium reduction method. In addition, to evaluate the impact of preceding winter crops on the yield of subsequent summer cultivation period, common bean crops were harvested 8 times. In the common bean crop of the first experimental year, the soil nitrogen concentration were at the highest levels just after the crop establishment. In addition, the nitrogen level decreased in all treatments, and at the stage of flowering, the higher levels were found in plots with organic broccoli as preceding winter crop. Then, the soil nitrogen decreased during harvesting, with lowest levels measured in plots with organic broccoli and fallow as pre-crop treatments during the winter. At crop termination, the soil nitrogen increased compared to the previous sampling dates, with lowest and highest values found in plots left fallow and cultivated conventionally with common bean following conventional broccoli cultivation respectively. During the second experimental year, 10 days after the crop establishment, the soil nitrogen concentration was highest in the conventional common bean crop. At the flowering stage, the plots of common bean established after the fallow resulted in lowest nitrogen levels compared to the other three treatments. During harvest period, the highest nitrogen concentration were measured in organic plots treated with green manure and plots with conventional common bean. Finally, at crop termination, the application of green manure resulted in highest soil nitrate levels than in the other three treatments. As far as the yield, the different applied treatment during winter had the same impact on yield of the subsequent common bean crop to both experimental years. More particular, green manure application enhanced the pole yield of the subsequent crop of organic common bean compared to organic broccoli as preceding crop. In addition, the yield of the common bean obtained from the plots with fava bean cultivated as green manure was similar to those recorded at conventional common bean crop. Concluding, the yield of common bean cultivated organically in the open field during summer, followed organic broccoli during the preceding winter, decreased due to the restricted soil nitrogen availability compared to conventional bean. However, the cultivation of common bean during the warm season, following a legume crop applied as green manure during the preceding winter, resulted in similar or even high soil mineral nitrogen level and similar yield with those found in conventional bean crop. The lowest mineral nitrogen levels during summer the second experimental year were recorded in the fallow plots, although the yield obtained from those plots was not significantly reduced compared to that obtained from plots cultivated organically or conventionally during the winter. Therefore, nitrogen availability is not the main but significant key factor affecting the productivity of the organic cropping systems. I would like to thank you for your time and attention, and I would like to mention that this work was supported by European Commission within the project through Transition Path to Sustainable Legume-Based Systems in Europe, which has received funding from the European Union's Horizons 2020 Research and Innovation Programme.
Hello to all the participants of the symposium. My name is Eva Bajon and I'm going to present my work titled Bolting Garlic Quality and Morphological Traits Are Influenced by Scape Removal. Garlic has been used in diet and traditional medicine. It is rich in organosulfur and phenolic compounds that give garlic beneficial health effects. Concerning its ability to flower, there are bolting garlic and non-bolting types of garlic. Scape removal in bolting garlic types is considered suitable to increase bulb yield. Istarski crveni and brsečki are Croatian landraces which develop floral scapes, have reddish clove skin color, smaller number of cloves, have good storage and overwintering survival, which make them interesting for production by local producers, and they are usually sold in braids, which means that the scapes are usually removed. The aim of this research was to investigate the effect of scape removal on morphological and physicochemical quality indicators in two Croatian bolting garlic landraces, Istarski crveni and brsečki. Both landraces were grown at the Institute of Agriculture and Tourism trial field. Garlic was planted in October 18 at a density of 38 plants per meter square at randomized complete block design in 4 replicates. The floral scapes were removed in the following spring when tips were visible between leaves, as can be seen here in the picture. It was harvested in the end of June and cured in the shadow. 10 bulbs per repetition were sampled for the observation of weight, diameter, height, and number of cloves. Dry matter was determined by drying 5 grams of peeled garlic at 105 degrees Celsius until constant weight. Total soluble solids were determined using a digital pocket refractometer. Firmness was measured with an electronic penetrometer equipped with a 50 kilo load cell and flat 3 mm bottom cylinder probe. A handheld spectrophotometer was used to measure clove coloration that determined 3 parameters: L for lightness, A for redness, and B for yellowness. 10 cloves per landrace were freeze-dried, lyophilized, and finely milled. The extracts were prepared either with deionized water for sugars or 50% aqueous methanol for the antioxidant capacity and total phenol content. Samples were sonicated, shaked, and centrifuged. The total antioxidant capacity was evaluated by ferric reducing ability of plasma and diphenyl picryl hydroxyl radical scavenging assay. And total phenolic content was evaluated by the Folin assay. Volatile compounds were analyzed using gas chromatograph with a flame ionization detector, and the amounts were presented as peak area counts. And sugars were quantified by high-performance liquid chromatography with refractive index detection. The data were processed by the analysis of variance using Statistica software. As regards results for morphological traits, brsečki has shown higher values for weight, height, and number of cloves. When scapes were removed, bulbs had shown higher weight, diameter, and height comparing to control. Concerning results for physical parameters, brsečki had higher redness or A value and lower lightness and yellowness comparing to Istarski crveni. When scapes were removed, total soluble solids and dry matter were significantly lower than bulbs where scapes were not removed. The results for sugars, total phenols, and the antioxidant capacity show that when scapes were removed, the glucose and the antioxidant capacity were lower and fructose was higher comparing to control. Concerning garlic volatiles, Brsečki and Istarski crveni differed significantly only in the content of allyl mercaptan and dimethyl trisulfide. Garlic with scapes had significantly higher values for 3 specific volatiles that are rounded here in the table, including the major compound diallyl disulfide. Based on our research, the practice of scape removal may be applied to the studied land races depending on the market preference, giving advantage either to bulb size or to certain quality parameters. Bolting garlic bulbs have smaller size and are unsuitable for making garlic braids due to the presence of the scape, but due to their quality may be preferred and used as spice or for medical purposes. Thank you very much for your attention.
Dear colleagues, thank you all to participate on this meeting. My name is Nina Kacian-Maršić, and with my co-chairman Rui Marchado, we're chairing the section Cultivation Practices and Agrotechnology. We are thankful for all presenters giving the main points, and during this session we have summarized some questions, and now I will invite Alexandra to answer the questions about your presentation. It's very valuable presentation, and the question is there any advisory service in North Macedonia paid maybe for by the state or by a private individual that provides a professional assistance to producers?
Yes, thank you very much. It's a pleasure to take part in the symposium. It is a very important question, and yes, there is a public service. It's called the National Extension Agency. So it is an organization that has been functioning for many years, and it's well spread across the country. So because we have a large number of farmers, it is very important for them to get an advice. And this is one of the mechanisms how to get them to get a good service with regard to extension. However, there is still a recognized need for better knowledge transfer in the system, and that remains a key challenge.
Mm-hmm. Thank you. And the other question is in North Macedonia, the connection between the research institution, maybe institutes, or education in the institution like faculties and producers.
Yes, thank you. I think this flows well from the previous question. Actually, there is in place some kind of agricultural knowledge information system. But it is true, there are a number of universities that are engaged in agricultural sciences. There is a line ministry that creates the policy. There is the extension service and the farmers, which all form this system. However, linkages can be improved. And coming from the research side, I have to emphasize that knowledge transfer should be enhanced further. And all these important parts of the system have their role in it.
Thank you. Thank you very much. Maybe from the audience, some questions?
Maybe I can add, Piotr had a private question in the chat, which was very interesting. How can the EU help advance the horticultural sector in our country? And I mentioned to him in the chat that one of the channels is the IPART program that we have running in the country. So there are a number of measures that address all kinds of issues in the sector with regard to structural issues. And the most important being are investments in physical infrastructure, both at farm level and at agri-food level, and diversification. Because farms are small, they have to tackle challenges through different strategies, and diversification is among the important ones.
Mm-hmm, mm-hmm. Yeah. Very interesting questions, yes. Another question?
Thank you for the attention. Thank you. Thank you for the answer.
Thank you. Very nice question and important one.
Okay. Thank you, Alexandra. Maybe the second presenter was Zvezda, and I prepared some questions also for Zvezda. Is here Zvezda?
Yes.
Okay. Your presentation, influence of mulching materials on pepper characteristics. We know that every year at the end of the growing season, there are many tons of black plastic mulch in the fields where fruit, vegetables are grown. How can growers deal with this waste?
Thank you very much, Professor Maršić, for the question. The mulching is not vastly used in North Macedonia, although worldwide it is a common practice. I agree that there is a lot of plastic mulch left, but so far our producers use the plastic mulch several seasons or times, and unfortunately after that they throw it to the landfills. So I hope that in the near future the growers will accept biodegradable mulch, which is environmental friendly, and so far as I know is available on the market in the neighboring countries.
Yes, I agree, but this degradable mulch is very expensive right now. Yes, yes. The straw from the mulch, which you also use in your research, is often incorporated into the soil at the end of the growing season. What kind of problems do you think may occur after the straw is incorporated into the soil?
Thank you very much for the question. Organic residue incorporation and straw mulch also incorporation, first of all, improves the soil physical properties and also after that yield. Crop residues addition is necessary for effective nutrient management availability, as well as minimizing the soil carbon loss. So incorporation of straw mulch can increase organic matter content or total organic carbon, which is very important. But initially, the straw addition can cause nitrogen immobilization, which is fulfilled by addition of inorganic nitrogen fertilizer. So the addition of mineral nitrogen speeds up residual mineralization by narrowing C/N ratio, which is high in straw mulch.
C/N ratio is very higher and does block the nitrogen mobilization. Yes, yes, thank you. Thank you very much. Maybe from the audience, some questions? If not, thank
I have one question.
Yes, please.
I have written to Zvezda, but maybe she's not
Sorry?
seen
Okay.
it. I have written one question, but I will repeat it.
Okay, thank you. But
because during the vegetation, there is a under the black mulch, especially from the film, polyethylene film, appears very high temperature because of the sun radiation. Okay, and so what is the result of it that the mulch is in very high temperature? Some sunburns? Did you observe some sunburns on the fruits or something like damages?
Thank you very much. From the results and the experiment, it is written, and we saw that the black mulch was the best for the pepper capia type production. So it might cause burns, but maybe in our case there wasn't problem with the burns on the fruits of the pepper.
Okay, and you have, sorry that I will prolong the question. Maybe with the tomatoes for processing, did you observe something like damages? You don't know knowledge.
Our experiment was about the pepper production. So when we are talking about tomato for processing, it is grown on the ground without support. So maybe it can be and can be some problems with the mulch, black film mulch, but I think that tomatoes form a big vegetative mass, so they cover the ground, and I think that maybe at the beginning of the vegetation there will be some negative effects, but after that I think that there would not be any problems with the processing tomatoes.
Okay, thank you. Thank you so much.
Nina, I'm very sorry to interrupt, but we have to plan carefully the time of our discussion, because we already spent half of the time with only 2 speakers. It will be fair to spare some time for the rest of them. Thank you.
Okay. Next, the next questions is for Piotr. Do you hear me? Do you hear me? Yes. Have you measured microclimatic parameters, temperature and humidity, and PAR intensity under the low tunnels continuously, or during on some days during the growing period?
Yes, I will be short. The measurements were provided some days only because of the short covering period. It was only 2 weeks. Establishing of experiment was in 3 replications. It was maybe the second part of the question. So that is the reason that it was accidentally.
And what microclimatic parameters do you think most influence biochemical changes in pepper fruits?
Could you repeat the question?
What microclimatic parameters, temperature, humidity, solar PAR intensity, most influence the biochemical changes in fruits?
Yes, understood. The most important for the plants and the finish effect of their quality is, in my opinion, sun radiation. It consists of the PAR, as we know, which influence photosynthesis, and near infrared radiation, which is transformed to the infrared. Actually, it influence on the temperature. So the final result is the higher or lower temperature around the plants. The temperature influence other factors like air and soil moisture, CO2 as well.
Yes, I agree. Thank you very much. Now I have a question for Eva. Do you hear me?
Can you hear me?
Yes.
Okay.
In your conclusions, you said that this measure of removing or not removing the scape in hard garlic varieties depends on market preference. What do you think? Will the customer in your country be willing to pay a higher price for garlic with higher allicin content, maybe?
Thank you for the question. Well, we know that the allicin compound gives aroma and taste to garlic, but also volatiles that are produced after the decomposition of the allicin give bioactive effects of garlic. And there is an overall trend in our region, in our area, where people tend to prefer superfood or food with health beneficial effects or healthy food and so on. And also people prefer to consume food and products that are produced from local varieties. And yes, I would say that people are ready to pay more for such product. And I think that it's already confirmed because our local producers usually sell all the amounts that produce. And also we are very, very touristic area, and which also means that we have a good market and we have a place to market our products. So I wouldn't say that people mind paying for quality, especially if it's something that is locally produced.
Thank you very much. And now I give the words to my co-chairman, Rui, please. Will you continue?
Thank you, Nina. Thank you, Nina. Good morning or good afternoon, everyone. First of all, congratulations to the speakers for their presentations. I also have some questions. For example, one para Boris Adamovic. Do you think the earliness due to the use of the tunnel compensates the costs of the low tunnels and must be recommended to the farmers? I don't know if Boris is...
Hello, everyone. Thank you for a question. The price of early watermelon in Republic of Serbia from low tunnel is higher for 10 to 15 euro cents per kilo than watermelon produced on polyethylene mulch, so farmers can cover the cost of the cover material.
Thank you.
Thank you very much.
I have a question for Cara Vidas. I don't know if it is present.
Yes, I'm here. Hello, everyone.
Hello. My question is, how was the fertigation carried out? The fertilizer applied by fertigation was applied several times, or in a single application?
In the organically cultivated common bean, the basal dressing included sheep manure, which provided 40 kilograms nitrogen per hectare, and 750 kilograms pounded kali per hectare. Moreover, no other fertilizers were applied at the organically cultivated plots until the end of the cultivation period. In the conventional grown common bean, an organic fertilizer was applied as basal dressing, which provided 55 kilograms nitrogen per hectare, and additionally at the stage of flowering until the end of cropping season, a nutrient solution was applied through the drip irrigation system to the conventional common bean crop, which provided 20 kilograms nitrogen per hectare. Therefore, the total amount of applied nitrogen was 40 in the organic and 75 kilograms nitrogen per hectare in the conventional farming systems, respectively.
But you did fertigation, yes, in conventional broccoli.
Ah, okay. Yes. Concerning the conventional broccoli, yes.
Yes,
okay,
yes.
As the conventional broccoli, again, we added the basal dressing using sheep manure at the beginning of the cultivation, before the establishment of the crop. And then at the conventional farming of broccoli, we added 1/3 of the total fertigation scheme as basal dressing. And then after the formation of the broccoli head, after 60 days after the crop establishment, we start the application of the nutrient solution till the end of crop season, and we apply the nutrient solution once per week.
Once per week. Okay, thank you. Thank you. I don't know if I have time for other questions. Okay, I have. I have a question for Zoran. Zoran, in my country, we grow potatoes in raised beds to minimize flooding. This technique can be a solution for you. I see in your slide you use also raised beds. Zora, are you present? Is you present? No.
Okay, I'm here.
Okay.
Okay, I'm here. I was muted. Thank you for the question. Unfortunately, in our country, there is no such type of potato production. I know it's very important in the situation of flooding or big water, and we don't have tradition for such potato growing. Also, our producers don't have equipment for such type of production, and also there is lack of knowledge for doing something that. I know it's very useful in this condition of flooding, but we never do on this way.
Well, another question: what was the growing media or soil used to grow the potatoes in pots?
Because we use the same growing media like in other research we do in protected structures.
Okay.
It's professional humus-based substrate. We buy it in agricultural shops. Nothing special.
Okay. Thank you.
Thank you.
I finish my questions. Thank you.
Honorable chairs, ladies and gentlemen, good afternoon. Although it is a pity that I cannot visit the beautiful city of Ohrid and attend the symposium in vivo, it's my great honor to present my work online. I'm Xun Li from Institute of Soil Science, Chinese Academy of Science. The topic today is the improvement of nitrogen use efficiency of cucumber plants by increasing the atmospheric carbon dioxide and root temperature in a greenhouse. My presentation will cover the following 5 aspects. First, I will introduce the development of greenhouse vegetable cultivation in China. Before 1990s, the greenhouse area in China is less than 80,000 hectares. Nowadays, China has the largest protected cultivation area in the world, accounting for 86% of the world's total area, in which the greenhouse vegetable area is more than 4 million hectares. However, the usage of nitrogen fertilizer is more than 1 kilogram nitrogen per hectare per year in China greenhouse for vegetable growing, and the nitrogen use efficiency is only 19.7%, which is much lower than that of the field crops. Our research group is trying to optimize the greenhouse environmental conditions to improve the nitrogen use efficiency of greenhouse vegetable, especially the CO2 concentration and the temperature in the greenhouse. Maintaining the high air temperature is the primary function of the greenhouse in China. In the cold winter, most greenhouses are not open or ventilated, so CO2 in the greenhouses is often depleted rapidly due to the photosynthesis after sunrise, whereas the light and air temperature are suitable for vegetable growth during the morning. So the lack of CO2 becomes one of the biggest adverse factors that restricts the absorption and the utilization of nutrients by vegetables, resulting in weak growth, poor yield, and low nitrogen use efficiency. On the other hand, although the air temperature in the greenhouse could be increased rapidly and reach the optimal range for vegetable growth after sunrise, the soil temperature changes less and is always below the optimal root temperature of vegetable in cold winter. Low root temperature restricts the expansion and the activity of vegetable roots, causes low transpiration, depresses the diffusion of inorganic nitrogen in soil solution. Accordingly, low root temperature is another biggest obstacle that limits the nitrogen use efficiency of greenhouse vegetables. In present work, we carry out 2 separated pot experiments with cucumber. The first one was conducted in 3 identical open-top chambers with 3 CO2 levels. The second one was conducted in 2 boxes filled with sand. The root temperature in one box was warmed by the heating wires embedded around the pots in the sand and set at 20 degrees centigrade. The root temperature in another box was under natural temperature. Each pot was watered with 1 liter nutrient solutions every 3 days with 4 nitrogen levels. The nitrogen use efficiency was calculated as the differences of the total nitrogen accumulation by upground between the treatments with and without nitrogen fertilization, then divided by the nitrogen input. The results showed that when the CO2 concentration was increased from C1 to C3, the increase in the dry weight was more than 100 in N3 level. The nitrogen concentration was decreased by 17.6%, but the total nitrogen accumulation was increased by 51.4%. The nitrogen use efficiency was increased by 88.3 to 10.9 percentage points by elevating the CO2 concentration from 400 to 1200 mmol per mole. The increase of dry weight by elevated CO2 is mainly caused by the increase of photosynthetic rate and CO2 fixation on the higher CO2 concentration, and the increase of nitrogen use efficiency by elevated CO2 appears to be a result of the increased rate of plant growth, which requires higher rate of inorganic nitrogen uptake and assimilation. In the root temperature control experiment, we found in N3 level, warm root temperature increased the dry weight by 91.7%, increased the nitrogen concentration by 28.2%, so increased the total nitrogen accumulation by 148.7%. The nitrogen use efficiency was increased by 11.6 to 18 percentage points by elevating the root temperature from 12 to 20 degrees centigrade. The improvement of nitrogen uptake and nitrogen use efficiency in higher root temperature have been reported in other plants, and at least 3 possible reasons were well documented. Firstly, the root structure with a large surface area was formed in a higher root temperature, which could explore and intercept more nitrogen from soil. Second, optimal root temperature could improve the root activity to absorb more nitrogen from surroundings. Thirdly, the nitrogen mineralization rate is increased by warming the soil, which makes more nitrogen available for plants absorption. From these 2 experiments, we can conclude that elevating CO2 could promote the nitrogen use efficiency of cucumber by 8 to 11 percentage points, which mainly relied on the increase of the dry weight, which required higher rates of inorganic nitrogen uptake and assimilation in higher CO2 concentration. Elevating root temperature could also promote the nitrogen use efficiency of cucumber by 12 to 18 percentage points, which was probably attributed to the improved root structure, higher root activity, and more available nitrogen in the warmed soil. At last, I will thank Professor Duan and our group members for conducting this experiment. I also sincerely thank Professor Gruda for introducing me to this symposium and giving me lots of helps. We also thank the National Nature Science Foundation of China for funding support. Thanks for your attention. Here is my QR code of my website in ResearchGate and my email. Welcome everyone to contact us for future cooperation. Thanks.
Hello, ladies and gentlemen. My name is Božidar Benko, and I will present you a part of our results conducted during 2018, named lettuce yield and nutritive value as affected by biopolymer microparticles application. First of all, an introduction. All of us knows that nutritive value of lettuce may be affected by different factors from the beginning or from sowing, seeding until storage conditions. That nutritional value could be enhanced by the addition of desirable compounds during the growth. It is important that these compounds should be readily available for the plant root uptake. This we may achieve by the encapsulation and the preparation of microparticles. Microparticles are extremely small capsules with or without different types of coatings. The aim of this research was to test the effect of different particles, different microparticles and suspension of Trichoderma viride spores on yield and nutritive value of soil-grown lettuce. Materials and methods. The trial was conducted during spring-summer growing period in 2018. Batavia lettuce variety Melina was tested, and the trial was set up to a completely randomized block design in 3 repetitions. Seed was sown on March 19 into heated greenhouse, and planting was done on April 24 with plant spacing 30 centimeters between plants and 30 centimeters between rows. Immediately before planting, microparticles were incorporated into soil with amount of 4 grams per plant. Manual harvest was done on June 6th and June 13th, and biomass and marketable rosette weight were determined. In the laboratory, dry weight content or dry matter content and total chlorophylls, total phenols and total flavonoids were determined, and also antioxidative activity was determined in the laboratory. Here on this few pictures we may see trial conduction from planting in the upper row, and also application or incorporation of microparticles into soil till harvest or technological maturity of lettuce and in down road. As I have stated before, different microparticles were applied. That was alginate microspheres and alginates chitosan microcapsules, and also Trichoderma viride spores suspended in saline solutions were applied. Here we can see the amount of chemical agent and number of Trichoderma viride spores in 4 grams of microparticles, which has been applied for each plant. Achieved results of biomass and marketable weight are presented in this table. So we may see that the highest biomass and marketable weight were achieved by the application of calcium and Trichoderma viride microspheres. Also, the highest rendement was achieved by copper and Trichoderma viride microspheres. The highest result of the highest marketable yield was achieved by the application of Trichoderma viride spores. The lowest marketable yield, as you may see, was achieved by the application of microcapsules with calcium and calcium Trichoderma viride spores. Nutritive value, the highest parameters of nutritive value, as you may see, is achieved by the application of calcium microspheres, and the lowest values were achieved by the Trichoderma viride spores. Contrary to that, the highest dry matter content was achieved by Trichoderma viride spores, and the lowest one by calcium microspheres. And to conclude, the application of different microparticles formulation didn't affect lettuce yield components compared to control, which was untreated. Trichoderma viride spores suspended in saline solution achieved relatively favorable effect on the observed yield components. The application of Trichoderma viride spores resulted with the highest dry matter content, but with the lowest content of phytochemicals. The highest phytochemicals content and the highest antioxidant activity were achieved by microparticles containing calcium ions and containing calcium ions and Trichoderma viride spores. This is the result of calcium role in phytochemical synthesis. The application of biopolymer microparticles could be recommended for the use and to achieve the higher nutritive value of lettuce. But there is also a need to test the assortment of lettuce or other vegetable crops under different agroecological conditions or different growing periods. Thank you for your attention.
Hello everybody. My name is Konstantinos Skitas. I'm coming from the University of Thessaly, Greece, and I will try to present you our work entitled Smart Greenhouse Production Practices to Manage and Mitigate the Impact of Climate Change in Protected Cultivation. This work was made by Professor Nazim Gruda and Mehdi Bizbis from the University of Bonn, Germany, and Professor Nicholas Katsoulas and myself from the University of Thessaly, Greece. The mean temperature shift under global warming will not only cause higher temperatures, but also an increase in extreme weather events. It is noticeable that 20 to 40% of total greenhouse gas emissions are attributable to the food systems, and horticulture is among the sectors that contribute to climate change, but is also among those that are affected by climate change. According to reports of the World Bank on climate change and agriculture for countries in the southern Caucasus region, an increased number of hot, dry and wet summers and hot, dry and wet winters is recorded last 30 years. However, midwinters and springs cause a lack of cold accumulation and sufficient winter chilling and vernalization that make early vegetables physiologically suffer. In summer, heat waves and drought restrict vegetables' yields, and the absence of precipitation will place farmers before difficult decisions. Facing these adverse environmental impacts on field crops, it will become more and more necessary to develop protected horticulture. In this paper, we focus on adapting protected horticulture technologies and practices to the adverse climate conditions that are triggered by climate change. Geographically, the focus is on the regions of southeastern and eastern Europe and Central Asia, where no data on protected cultivation of vegetables exist and where most greenhouses are rudimentary equipped. Protected horticulture includes mini and walled-in tunnels, plastic and glass houses, and screen houses. The protected systems vary from a very low degree of technology to high-tech constructions. However, environmental burdens are not excluded in protected cultivation. Particularly, heating and cooling becomes an even bigger burden in terms of energy and water consumption. Therefore, clean technologies in terms of energy and water consumption, as well as cultivation practices, are required. The challenges towards sustainable, smart, protected horticulture are for greenhouses the proper choice of the location, the design of their climatization, the energy saving, the IPM technologies, the rational management of water resources and hydroponics, the smart climate control, and furthermore, the development of screenhouses and other measures such as breeding new cultivars, avoid food waste, etc. In order, the first step for greenhouses development is the characterization of regional suitability for greenhouse cropping. This characterization is made by climographs. As an example, I give you here the climograph of Baku, Almeria, and Amsterdam, and we can see that Baku during winter has a climate similar to Amsterdam, and during summer similar to Almeria. Those greenhouses in cold semi-arid climates should be equipped with heating in winter time, but also with ventilation, shading, and active cooling during summer. The climatization systems are the following. For heating, we can heat with metallic pipes or aerotherm heaters. For ventilation, for cooling, we can use either natural ventilation with lateral and roof openings, either evaporative cooling systems, the fan and pad cooling systems, or the fog system by spraying water inside the enclosure. Shading, the shading factor, the most convenient is 20 to 4%, and the shading could be made either by whitening or by net screens. All the above systems can be exactly dimensioned through available softwares existing in our laboratory, but also elsewhere. Passing to the energy saving, different methods exist. The most appropriate are the thermal screen, the use of renewable energy sources, biomass, here a greenhouse heated by olive kernel in Volos, Gardenia greenhouse. Also, the idea of the closed greenhouse, where we harvest energy during summer and we reuse this energy stored during summer, and we reuse this energy for heat the greenhouse during winter. Other also prototypes for the same idea, for harvesting and reusing energy using underground soil as a buffer, are developed and constructed with excellent results in Greece and Cyprus through the European program Adapt to Change. The IPM technologies, in order to reduce chemical for phytoprotection, are screens, but also UV absorbing materials and also anti-drop, anti-fog covering materials, because these materials reduce fungicide use and spraying. The management of water is very important in the hydroponics also, because we have high inputs in water and fertilizers in greenhouses. As an example, 4,500 liters of water are yearly consumed per hectare in Mediterranean greenhouses. In order to reduce these quantities, we can either make by rational use of water through models, decision support systems, and sensors, either by development of hydroponics, which is a method very efficient in order to increase the quantity, the quality, and increase also the water use efficiency. As an example, I give you here a decision support system developed in our laboratory for the intelligent water management, the program of PIRIS, and with these systems we take measurements from different greenhouses over the world, and using the web-based models, we calibrate this model with the measurements, and we can propose to each producer irrigation scheduling program for the next 5 days. For the greenhouse climate control, we must pass from the conventional climate control, where air temperature humidity is measured only at a single point in the middle of the greenhouse, to a more intelligent greenhouse climate control in order to characterize intra-greenhouse climate distribution. And so we have to move from sensors, for the sensors, we have to move from the traditional strategy of monitoring one variable in the center to monitor as much variable as many points we can. Here I show you different sensors for climate variable, but also in the bottom, new wireless systems developed in our laboratory for characterizing the distributed climate inside the greenhouse. This greenhouses is very important to develop, because during summer the crops face major problems for missings, high water consumption and degradation of the crop quality. And this greenhouses is very simple agricultural construction with net cover, low cost, lack of automation, and we have either shading nets, either insect-proof nets greenhouses. And several experiments show that greenhouses improve the climate, increase the marketable production by 100%, and also reduce the water consumption by about 40%. And the most appropriate shading factor is 20%. Finally, other important measures that can accompany the previous technological methods is the breeding new resilient cultivars with stable yields and high product quality, the use of genetic materials coming from local biodiversity, avoid food waste, both in production and consumption, and greater public and private investments in technology and human resources, and also well-balanced diets with fruit and vegetable portions are very important. So, as a conclusion, we can say that the technologies for smart greenhouse production exist. However, the greenhouse microclimate control must combine efficient sensing of climate crop variables, appropriate dimensioning of the heating, ventilation, and cooling system, choice of the appropriate system and intelligent control of the systems, but also regional institutions should conduct holistic and long-term research focused on irrigation and water management, and on energy saving and clean energy careers, development of greenhouses, breeding programs on resilient genetic materials, and plant protection against domestic as well as newly occurring pests and diseases. Thank you for your attention.
Thank you for the opportunity to present our work in this virtual ISHS meeting. My talk will deal with a model of circular economy to be applied to greenhouse productions. Greenhouse cultivation can give multiple benefits for the productivity of high-value crops. In addition to high yield, it can guarantee year-round production, the cultivation in unsuitable fields, and can reduce the transportation needs, shortening the field-to-fork steps. These aspects can increase the value of the production and therefore the farm competitiveness. However, protected cultivation implies high energy inputs for temperature control, for lighting, for pumps, and for all the automation systems necessary for its correct functioning. The expense for energy can account for more than 50% of the total cost of the greenhouse. Moreover, the production of energy is the first sector for CO2 emissions, accounting for more than 70% of the total CO2 equivalent emitted worldwide. The 80% of energy production relies on fossil fuels, which are not renewable and have an important ecological footprint. Indeed, fossil fuels are one of the main causes of climate change and should therefore be replaced by renewable resources. Energy costs and the overall environmental impact of greenhouse production can be reduced by shifting from fossil fuels to biomass-based systems. Indeed, biomass from agriculture and forestry can be used as renewable resources instead of being disposed with additional costs for the farmers. If needed, biomass can be also produced on marginal lands where the production of agricultural crops is not an option. The technologies for the production of energy from biomasses are constantly evolving, seeking efficiency and sustainability. One of the most promising solutions for biomass conversion is the cogeneration, that is the combined production of heat and energy from biomass-based fuels. Thanks to this system, the efficiency of energy production is high and eco-friendly. Once biomass enters the cogeneration plants after pyrogasification, it is transformed to heat and energy. Energy can be used to fulfill the energy requirement for the greenhouse, while heat can be used for temperature control. This increases the sustainability of the production since it needs less inputs of fossil fuels. More interestingly, the byproducts of the process, namely biochar and CO2, can be used for greenhouse productions. Biochar is the carbonized biomass at the end of the process of gasification, while CO2 is produced because of the burned material. Therefore, the byproducts of cogeneration represent an added value for agriculture, since CO2, once captured and stored, can be used for carbon fertilization in the greenhouse. On the other hand, biochar is a well-known soil amendment, frequently used in the agricultural context and known to improve several aspects of the plant soil system. The use of these two byproducts for greenhouse production allows to reduce the CO2 emissions, since the enriched CO2 will be assimilated for photosynthesis by plants and can improve plant growth thanks to the synergic action of biochar amendment and CO2 fertilization. This will improve the production efficiency of the whole process. CO2 enrichment in controlled environment is able to increase the productive and the physiological performances of plants, as evidenced by several scientific papers. In our bibliographical survey, we reported the beneficial effect of CO2 supplementation in 18 different species grown under controlled environment. The main responses are higher growth and productivity and improved flowering. By a physiological point of view, as expected, plants growing under supplemented CO2 showed higher photosynthetic rates and a higher resource use efficiency in terms of water and nutrients. Moreover, these plants showed higher tolerance to abiotic stresses like drought and salinity. Finally, CO2 enrichment has been reported to prime plant defense systems thanks to the increase of salicylic acid and antioxidant in plant tissues, improving plant tolerance to biotic stressors. Therefore, CO2 enrichment increased crop productivity, resource use efficiency and defense, with benefits in terms of productive efficiency and product quality. In a similar way, biochar amendment has important benefits on different aspects of plants and soil parameters. In the figure from the study of Biedermann and Harpel, the benefits induced by biochar amendment are in red circles, which are the parameters that are significantly improved as compared to the controls. According to this meta-analysis performed on more than 300 different studies, biochar amendment was shown to improve plant growth, yield and the nutrient use efficiency, as well as favored the formation of rhizobia nodules. Moreover, biochar increased the soil macronutrient and carbon content, as well as the soil microbial biomass. Taking all these aspects into consideration, we propose the green farm modular system as a perceivable way to implement the principle of circularity in agriculture, since it allows a more rational use of resources, making value from all the wastes resulting from the production process. The figure exemplifies this concept. Both greenhouse organic waste from the left and the biomass obtained by the dedicated field on the right will be sent to the energy conversion facility in the middle of the image. There, energy, heat and CO2 are produced and used for greenhouse management. Finally, biochar amendment can be performed to the soil, both in the greenhouse and in the biomass field, increasing their productive performances. In summary, it is pivotal to reduce the impact of energy production, and cogeneration from biomass can be a perceivable opportunity for the agricultural sector. Since cogeneration byproducts are employed for production, the implementation of circular economy principle could be satisfied, thus achieving higher economical and ecological sustainability. Thanks for your attention.
this was a long but very interesting session. We all know that the greenhouse technology is the cherry of the cake of the vegetable production. I'm very sorry that we do not have present here our dear colleagues from China. There is a big time difference. However, we have some sufficient audience here. I will have to excuse our announced chair, Professor Konstantinos Kitas. He had some health problems, so I will take his place. And I will abuse this place immediately by making some questions before giving the floor to the my co-chair, respected colleague Božidar Benko from Croatia. My first question is for you, Božidar. We all know that the salad, as other leafy vegetables, tends to accumulate nitrates.
Yes.
In your experiment, can you please tell me, maybe I have missed, but I didn't see if you have analyzed the content of the nitrates in respect to the nutritional schemes.
No, but plant material wasn't analyzed for nitrates. This was a part of a research for a master thesis, and this kind of analysis were not planned in this research.
Yes, you maybe you will agree with me, Božidar. The conclusion of the very first presentation from our colleagues from China indicated that the higher temperature stimulates the nitrogen mineralization. So in the previous sessions, in the first working session we had, there was much discussion about mulching materials and what would be their impact if the high temperature reflecting from the mulch would affect the fruit vegetables that mulching is used for, but obviously it affects also the mineralization of the nitrogen, and if the temperature is too high, it may, in the case of leafy vegetables, especially lettuce, produce some adverse effects, if you agree.
But as you have seen in our presentation, mulch wasn't used. There was no mulch in this research. Salad lettuce was planted on bare soil.
Yeah, I see. About the presentation of our dear colleague Sanja Radman. Is Sanja here?
Here. Hi.
Nice to see you, Sanja. I've noticed that the electrical conductivity that you used for both your treatments was very, in my opinion, a little bit lower than usually. It was 5 point something. Is it common for?
No. pH value was 5.8.
Yeah, I'm speaking about pH.
Yeah, okay. You said electrical conductivity, so
my mistake.
Sorry. Okay.
Yeah.
You said that it was too high.
Too low.
Too low. No, but singing nettle is like vegetables. I think it's okay for nettle production.
So it's not acidophilic, let's say, I'm speaking about urtica. Because at least in our region, in my country, it's not common to cultivate, to cultivation. Urtica is all considered as a weed. We don't use it for salads yet.
No, it's not like salad. This is maybe it's problem to understand this research because it's next phase, this hydroponic cultivation of nettle. But before we had also research about introduction of nettle in agricultural production, because we don't know what this material from natural habitats has minerals, nitrates, and heavy metals and problems. So this is the next level of our research with nettle. This is hydroponic cultivation, and we use 2 nutrient solution, and they have pH value in that rank, but in our research it was a little bit higher, so about 7.
So,
it was not too low. I think it was not too low.
You're going to use this plant as for remediation of the soils afterwards?
No. We use nettle like vegetable. Not for
consumption.
Yes, for consumption.
For fresh consumption.
Yes.
Thank you. And finally, Valerio. Very interesting concept. But I think that biochar is almost used like antibiotic with a broad spectrum, you know. It heals everything, it gives higher yield. Did you have any specific trials actually with use of biochar? I'm interested because I'm supposed to start a project with biochar now, and I would like to know what are pros and cons of biochar application.
Thank you for the question. I've never personally used biochar for my experiments, but in that review that I put in my presentation, there are more than 300 papers in which they found beneficial effects on different aspects. So I think the most interesting one could be the trigger of the defense system of the plants that somehow can help in reducing the pesticide spread in plants, in cultivations. But also on the soil properties, it has very useful because it can be useful because it can increase the carbon content of the soil, and so all the organic matter in the substrate, and this can improve all the quality and the ability of the plants to take these nutrients up. And I think it's a new aspect of plant cultivation that should be studied in deep, because it's a natural product and can be multi-phased, can have a multi-phased effect on plants.
Thank you very much.
You're welcome.
Now I would give the floor to Božidar. If you have some questions.
Yes, okay, I also have a question for Valerio. This question is continuing your question, Gordana. Valerio, what do you think about biochar use as a soilless substrate? Not like a soil amendment, but like a soilless substrate on its own. Is it possible?
I think the amount needed to fill a pot with just biochar that is like a little powder could be hard to use, I mean, in a logistical way. But maybe I don't know how much it can retain the water and which are the properties of biochar as a substrate. So, but maybe it can be, for soil amendment, it has for sure good properties because it's a carbon source
that is always beneficial for plant growth. I don't know if after a certain threshold it can have some detrimental effects on plant growth or on root development, but it's something that we should go in deep and study better.
Thank you.
Thank you so much.
Maybe we can conclude the discussion. I just want to say to you and to the audience, to the previous participants, that our web page is open for questions, because this recording of the symposium, both the first and the second day, will be available on YouTube for the following week ahead. So if there are any additional questions, we will gladly address them to the respective authors, and we'll get back to you with the answers. So thank you, and see you in the next session.
Thank you.
Dear colleagues, my name is Dr. Neshu Neshev. I work at the Department of Agriculture and Herbology at the Agricultural University of Plovdiv, Bulgaria, and I'm going to present the study Recovering Effect of Biostimulant Application on Pumpkins Treated with Imazamox. The experiment was situated in the experimental field of the base for training and implementation of the Agricultural University of Plovdiv, Bulgaria. The pumpkin variety grown in the study was Matilda F1. To remove the weed pressure to the crop before planting of the plants, all experimental plots were covered with polyethylene mulch. Before mulching, drop irrigation system was built. The study included the following treatments. Untreated control is the first one. At treatment 2, application of Pulsar 40 grams per liter Imazamox in the third true leaf on May stem unfolded of pumpkin plants was performed. That's BBCH 1315. The herbicide Pulsar 40 is registered for imidazole tolerant sunflower and oilseed rape hybrids from the Clearfield technology of the company BASF. The treatments 3, 4 and 5 included 2 applications, first by the mentioned herbicide Pulsar 40 and second medicative biostimulant applications 7 days after the herbicide treatment. The products with biostimulant mode of action used in the study were as follows: amino expert impulse containing amino acids, phytohormones, organic substances, natural adhesives, micro and micronutrients. Aminozole contains organic substances obtained from animal subproducts, protein hydrolysates, nitrogen, potassium, sulfur, etc. Terasol complex contains 3 amino acids, macro and micronutrients. The visual phytotoxicity on the 7th day after herbicide application was determined using the 9-score phytotoxicity scale of the European Weed Research Society. From 1 to 9, different numbers are equal to some different phytotoxic symptoms like stunt effects, yellowings, like sclerosis, and etc. Biometrical analysis, total leaf area and phenological observations were performed, like fresh biomass of one pumpkin plant in phenophase botanization with BBCH 59, number of leaves per plant in BBCH 59, total leaf area in phenophase BBCH 59, beginning of flowering BBCH 61, number of fruits per plant, and total productivity of the plants, tons per hectare. So the aim of the study was to evaluate the therapeutic effect of biostimulant application on pumpkin plants treated with the herbicide Imazamox or the product Pulsar 40. On figure number 1 is the visual phytotoxicity 7 days after the treatment in scores by European Weed Research Society. It was found that plants have stressed, like stunning effects and yellowing of the younger leaves, but the medicative and therapeutic application of biostimulants decreased the phytotoxicity, and later in time it disappeared. In the highest phytotoxicity levels were recorded for the alone application only with herbicide, score 2 in 2017 and 3 in the next 2 years of the study, 2018 and 2019. On picture number 1 are the plants from the untreated control. Picture number 2 is our plants treated with Pulsar 40 without biostimulant application, and you can see the plants are stunned and younger leaves are yellowing, and the plants are going to be recovered more difficult than the other plants with biostimulant application. Plants treated with pulsar 40 and aminosole 7 days later are on this slide. You can see the habitus of the plants is better and plants look healthier. And aminoexpertin pulse after pulsar 40 is on this slide. You can see no yellowing of the plants. On table number 1 is the fresh biomass of one pumpkin plant in phenophase botanization. It was found that plants treated with pulsar 40 and Terrasorb, as well as pulsar 40 plus aminoexpertin pulse, had higher values than the plants treated with pulsar 40 only, and the plants these plants had equal values like the untreated control. Number of leaves per plant in phenophase botanizations is on table number 2. You can see the lowest results are found for the treatment number 2, where only herbicide is applied. The same tendency is observed for the total leaf area per plant in phenophase botanization. Those variants with medicative biostimulant application has equal or higher results for the total leaf area as the untreated control plants, and pulsar 40 had the lowest values. Total productivity of the plants is presented on table number 4. You can see the highest results for the productivity was found for the pulsar 40 and therapeutic application of aminosole, 13.8 tons per hectare, and the untreated control had lower values, and the lowest results were found for the pulsar 40 treatment without medicative application. And the conclusions that can be made from the study: the application of herbicide pulsar 40 in rate of 1 liter per hectare caused with toxic symptoms to the pumpkin plants, such as stunning and just visible to visible yellowing and delay of beginning of flowering. The therapeutic biostimulant application showed protective effect on the herbicide-stressed pumpkin plants. The plants treated with Terrasorb complex after the herbicide application had the highest results for the total leaf area in botanization stage. Pumpkins therapeutically treated with the biostimulant aminoexpertin pulse had the highest results regarding the fresh biomass of one pumpkin plant and number of leaves per plant in phenophase botanization. The obtained results indicated that application of aminosole 7 days after the herbicide helped the pumpkin plants to develop higher number of fruits and higher productivity among the treated variants. And finally, I would like to thank you for your attention.
Warm greetings to everyone. My name is Marin Cukrov, and hereby I, in behold of a group of authors, present the examination of the effectiveness of grafting and biostimulant application as a strategy for enhancing tomato nematode resistance. Root knot nematodes infest a wide range of crops and are increasingly more difficult to suppress using traditional practices such as crop rotation. It is estimated that worldwide annual crop losses exceed $78 billion due to the soil-borne pathogen infestation. Nematode gall formation restricts root function, which results in stunted growth and flowering. With regards to tomato, this causes losses in yields over 30 to 65% depending on the cultivar in question and the infection intensity. Restrictions in the use of agrochemicals, such as methyl bromide, triggered the need for alternative strategies in suppression of the latter pathogens. This caused a re-examination of vegetable grafting as a strategy for enhancing plant resistance to biotic stress. Since it is a rapid alternative to the time-consuming breeding for nematode resistance, it provides the possibility of combining the inherent pathogen resistance of rootstocks with signs of desired characteristics. Adverse effects of agrochemicals on the environment in general also prompted a proliferation of various biostimulants and bionematicides with seemingly suppressive effects on root knot nematodes. Therefore, our research aims was to assess the effectiveness of certain tomato rootstocks in enhancement of tomato root knot nematode resistance, evaluate the influence of certain biostimulates with ostensible root knot nematode suppressive activity on the physiological parameters of tomato plants, and determine the ameliorative potential of combined implementation of grafting and biostimulant amendment against nematode infestation. The experiment was conducted in a 50-meter square heated chamber inside the experimental greenhouse at the Institute for Adriatic Crops and Karst Reclamation in Split, Croatia. Due to its resistance to tomato spotted wilt virus, tomato cultivar Matissimo F1 was selected as a scion, and the experiment featured 3 grafting combinations: self-grafted Matissimo as a control group, Matissimo grafted onto cultivar Arnold, and Matissimo grafted onto cultivar Maxford. Half the plants were infected with nematode larvae by placing the same amount of previously infected and segmented roots with visible galls to the growth medium. Plants were irrigated with regular tap water and connected to the drip irrigation system, through which we applied half-strength nutrient solution prepared according to Sonneveld. 2 biostimulant treatments were separately applied, Intera and Kendall Nem, and both biostimulants are declaratively promoting physical endurance of roots and enhancement of plants' natural ability to withstand biotic stress from nematode infestation, without having any direct nematicidal effects. Variants consisted of rootstock selection, biostimulant treatment, and nematode infestation, and were all represented in 4 applications on the basis of random block design. During the trial, the following parameters were measured: shoot length, leaf number, chlorophyll content, relative water content, specific leaf area, fruit number, and early yield. At the end of the trial, root nematode gall index was assessed with a scale from 1 to 5, according to standardized protocol by Jepson and Associates. Multiple differences in plant performance under nematode infestation were recorded, all depending on the combination of rootstocks and biostimulants used. Shoot length was under high influence of rootstock during the initial stages of development, at 28 days after planting, whereas in later stages, 64 and 80 days after planting, the effect of biostimulants was more pronounced. The rootstock biostimulant interaction revealed highest shoot length in self-grafted plants treated with Kendall Nem at 64 days after planting. Simultaneously, the main interaction revealed significantly highest leaf number in infected plants grafted onto Maxiford rootstock and treated with the Intera biostimulant. Regardless of rootstock and biostimulant used, Nematode-infected plants showed significantly higher stem and root dry weights. Early yield was highly influenced by all three factors, showing infected plants grafted on Arnold rootstock and treated with candle NAM, recording highest values, a total of 3.5 kilograms per plant, and surpassing even those of non-infected treatments. Whereas the nematode gall index proved to be lowest in plants grafted on Arnold rootstocks with the value of 0.39, whereas plants grafted on Maxifort showed highest nematode gall index of 1.61. Also, no significant difference in NGI between the applied biostimulants was recorded. Therefore, based on the NGI data, rootstock selection proved to be crucial for preserving plant resilience. Roots of plants grafted onto Arnold rootstock had the lowest presence of nematode galls, thus differing significantly from plants grafted to Maxifort and those self-grafted onto Matissimo rootstocks. Although having no suppressive side effects on nematodes, due to its performance with rootstock Arnold, Candle NEM biostimulant managed to maintain plant vigor and preserve continuation of physiological processes, which later reflected on the highest recorded values of yield. It would seem that Intera treatments could not alleviate the limitations caused by the biotic stress as much as Candle NEM treatments did. When applied to the best performing rootstock, Arnold, infested with root knot nematodes, yield was significantly severed. To conclude, rootstocks had greater influence than biostimulants over the enhancement of plant capabilities for coping with root knot nematodes. Candle NEM treatments combined with Arnold rootstocks managed to provide highest early yield even under nematode infestation. Therefore, rather than relying on the suppressive side effects of certain biostimulants, whose effectiveness against root knot nematodes should first be clearly defined and clarified, by now the use of tolerant rootstocks would seem to be a more practical tool for sustainable root knot nematode management. And with that, I thank you for your attention.
Hello everyone, I am Professor Mfail Salia. I come from University UBT from Pristina, Kosovo. My presentation is preventive agrotechnical measure in their impact on the occurrence of anthracnose disease among paper plants. Vegetable cultivation in Kosovo has been a tradition for hundreds of years. Paper crop occupies the largest area in vegetable cultivation among the vegetable cultivated in the country, especially in the western and eastern region of Kosovo. Apart from agrotechnical measure, the main concern of the paper producers remains its disease and pest protection. The biggest problem in the past presented Phytophthora capsicum and Pythium sp. From 2013 onwards, the Coledotrium sp. pathogen, which caused sporadic infection in the pest only during wet season, and where paper planting plants was a monoculture, has increased in intensity. The objective of my study was, under one, the role of the application of agrotechnical measure in the prevention of Coledotrium capsicum pathogen, extending our experiment to variants. the traditional cultivation variants and the variant involving application of advanced agrotechnical measure. Under 2, diagnosis of Colathetrium sp pathogen by microscope and microscopic method and measurement of infection intensity in cultivars put to the test planted in both variants. To achieve the first objective, we monitored agrotechnical measure from the time when the seeds were sowed in the classical way with traditional method. By sowing seeds in hot planting beds for all cultivars, the sown seed was of certificate type. Material and methods. During our research regarding the occurrence of the pathogen Colathetrium capsicum, the causes paper anthracnose, we have identified and diagnosed the pathogen by microscope and microscope methods in laboratory. The morphological identification of the pathogen was made based on the shape of the conidia determined by microscope analysis. Our experiment took place in the region of municipality of Rauves during the 2018 vegetation period. In the experiment, we included experimental files of some paper cultivars such as Babura, Bessiana, Dugabella, Somborca, and Red Caldura. The seedlings were treated through irrigation just after emergence with the fungicide Previcor with active materia Propomacarb plus Fossetil. This fungicide, which has been used for decided in this region as the most effective chemical combination against Pythium sp and Phytophthora sp in the early stage of seedling development. At the same time, we monitored the seeds of the same cultivar subjected to advanced agnostical method in the professional modules and substrate. Also, treatment with the fungicide Previcor energy was applied during the cotyledon phase after seedlings emergence. The transplanting started on 12 May to 16 May. The number of plants per hectare in traditional parcels was about 70,000 plants, while in the parcels with advanced agrotechnical the number of plants per hectare was 35,000. Monitoring and sampling of plants in the open field was done every 15 days, starting from June to October. Sampling was done on the same dates as in the traditional planted parcels as well as in those planted with advanced agrotechnical measure. At the beginning of the vegetation stage, we have sampled the level in the advanced phenological stage after the fruit settings. We have also sampled the fruits which showed symptoms. Samples taken from infected levels and fruits were sent to the laboratory for microscopical diagnosis of the possible presence of the pathogen Colathetrium. Here we have picture. We have the photos from the experimental plot, and in the other photos the fruit with symptoms of anthracnose. And here we have the reproductive organs of pathogen, their morphological conide with conidiophore, E and acervule. Discussion. From our experiment, we have concluded that the Colathetrium capsicum pathogen affects all cultivars with different intensity. This conclusion has been proved by laboratory analysis where the morphological identification of the pathogen through reproductive organs, conidia, has been done with the microscope method. This experiment showed that the application of agrotechnical measure is the best way to prevent plant infection. Seed sowing in professional models and substrate compliance with planting distance and moderate watering of plants are the decisive factors in the occurrence of infection with Colotridium capsicum. The behavior of the cultivars against the pathogen was different in both variants of our experiment, not only due to the fact of different agrotechnical measures used, but also due to the different resistance that the cultivars have shown each of the variants. Cultivar Ducabella with 3 positive samples from 100 samples, and Samborca only 4 positive samples from 100 samples. In both variants, Ducabella and Samborca cultivars have shown most resistant to the Colotridium capsicum pathogen. Conclusion. Based on the data obtained through this study, we concluded the Colotridium capsicum pathogen affected all tested cultivars. The variability of resistance is different among different cultivars. The variant where advanced agrotechnical measure were applied has been more successful in preventing infection and serves as the most effective preventive measure against Colotridium capsicum. Babura and Rancardula cultivars turned out to be the most sensitive cultivars in both variants. From our experiment, we also concluded that the Ducabella and Samborca cultivars are the most resistant cultivars over agroecological conditions. The analysis of variance proved that there are statistical difference of different levels of significance in terms of the presence of anthracnose disease among different cultivars. Thank you for your attention.
Hi everyone, my name is Hatice Özak'tan. I am from Ege University, Izmir, Turkey. I would like to share my presentation titled as Development of Biopesticide and Biostimulant Formulations for Good Agricultural Practices in Greenhouse Cucumber Cultivation. Greenhouse production is generally located on the coastal region of Turkey. About 87% of the greenhouse production area in Turkey is located in Mediterranean region. The most important problem of cucumber cultivation is Fusarium oxysporum homospecialis cucumarinum, which is a soil-borne fungus, causes wilting and death of cucumber plants, and fungus colonize the xylem vessel of cucumber plants systemically and causes vascular discoloration. It is difficult to control of FOC because this plant pathogen could cause systemic invasion. There is no resistant cucumber cultivars to this pathogen. Biological control has been considered as a potential method for controlling this kind of plant pathogens. The use of endophytic bacteria to control of plant pathogenic bacteria and fungi are receiving increasing attention as a sustainable alternative synthetic alternative to synthetic pesticides. You can see on this slides sampling and isolation process for endophytic bacteria, both from greenhouse and field, and we applied some special isolation techniques to obtain endophytic bacteria, such as filtration and imprinting of plant tissues. And then we applied some in vitro and in vivo tests for screening promising endophytic bacteria strains, both biocontrol of FOC and growth promotion of cucumbers, such as siderophore production on glucose agar medium, phosphate solubilization activity, indole acetic acid production activity, hydrogen cyanide production, seed vigority test, in vitro biocontrol activity, and in vivo biocontrol and growth promotion activity. The final goal in the biocontrol studies is to obtain bioformulations with high stability and effectiveness. The main aim of our study was to provide the commercial use of endophytic bacteria which were successful for biological control and growth promotion of cucumber cultivation. You can see on this table selected and promising endophytic bacteria strains, both for biocontrol and also growth promotion aspects. These selected endophytic bacteria strains effectively inhibited fusarial wilt in greenhouse and increased the total marketable cucumber yield. On the other hand, these strains showed very strong antimycotogenetic activity against potato weed larvae and some bacterial plant pathogens. The first step to obtain bioformulation is to grow them in cheaper substrate as scale-up production. Endophytic bacteria strains were grown on cheaper substrates such as molasses, corn syrup, soy flour, skim milk, heated bakery yeast extract. First step, we produced them in rotary shaker, and after as soon as we obtained the results, we started to scale up process, and we produced them in 10 and 100 liter capacity bioreactor. You can see our 10 and 100 liter capacity bioreactor systems. Endophytic bacteria strains were grown in cheaper substrates in 10 liter capacity reactor. And this table shows us the comparison of bacterial biomass of endophytic bacteria strains as a result of scale-up production, both in nutrient-broad medium and cheaper substrates, in rotary shaker and in 10 and 100 liter capacity bioreactors. As you can see on this table, our endophytic bacteria strains effectively grown in cheaper substrates comparing to nutrient growth medium. You can see on this slides formulation process of beneficial bacteria. First of all, obtained bacterial biomass separated by a separation equipment and then resuspended and then we applied freeze drying process to obtain edible powder bioformulation packages. And we monitored the shelf life of our bioformulations for 6 months, and most of them effectively survive both at room temperature and at freeze. And then we tested their effectiveness on cucumber plants as biocontrol agent and plant growth promoters. Endophytic bacteria formulations applied as seed coating and soil drenching, and endophytic bacteria-treated cucumber plants were transplanted to FOC inoculated soil, and weed development was recorded 24 days after transplanting to FOC infested pots using 0.4 scale. The effect of endophytic bacteria formulation on growth promotion of cucumber plants were also evaluated by weighing the fresh and dry weight of shoots and roots of endophytic bacteria treated plants without any disease pressure. And this table shows us the effects of endophytic bacteria formulations on Fusarium oxysporum formospecialis cucumerino and growth promotion of cucumber plants by pot tests. As you can see on this table, endophytic bacteria formulations exhibited the Fusarium yield reduction between 22 to 82% compared to only FOC inoculated plants. And the most promising endophytic bacteria treatment was Pantoia agglomerans strain 83. This strain, without being any disease pressure, increased the total marketable, fresh shoot and dried shoot and root biomass compared to non-treated negative control plants. These pictures show us effective bioformulations against Fusarium oxysporum formospecialis cucumerino compared to only FOC inoculated plants. Treated plants didn't show wilting symptoms. And some of our bioformulations positively affected plant growth and plant biomass compared to non-treated control plants. In conclusion, in this study, it was proved that tested formulations of endophytic bacteria strains were found very promising for plant growth promotion and biocontrol parameters. The results of our previous study indicated that endophytic bacteria strains 83 and 99 produced indole acetic acid, siderophore, aminocyclopropan carboxylate deaminase, and solubilized phosphate for plant growth. Endophytobacteria strain 83 and 99 not only significantly improved plant growth of cucumber, but also when used for seed and seedling treatment, significantly reduced disease symptoms of Fusarium wilt on cucumbers. So the application of edible powder formulations of endophytic bacteria strains at the concentration of 8 to the 10 to the 8 SFU per milliliter as a seed coating and soil drenching was recorded as effective and practical techniques in terms of biological control and growth promotion of cucumber plants. And our work continued with a commercial application of our bioproducts in growers' greenhouse. And you can see some part of our research team. Thank you very much for your kind attention.
Hi, everybody. My name is Ayşegül, and my co-chair is Neshe. Firstly, we would like to thank to all of you for your participating in the last session of today. I know all of us are tired, but it is worth to follow these interesting presentations. I would like to thank the authors for sharing their studies with us. Now I would like to give the floor to Nesho for discussion. Thank you.
Thank you very much. I also want to thank to everybody. You have done a great job here. A lot of work is done. So we have to continue with the questions now, or in the discussion. So first, if somebody wants to ask me some questions, because the presentation was in the session, or some of the participants here. Maybe not. Professor Popsimonova, if you have some.
Well, I have to admit that my specialty is also not really plant protection. I want just to express my gratitude to the participants for their excellent presentations. Maybe Professor Hatice Ozaskan can kindly give us some more information about the conclusions, because they were pretty much elaborated, but we can hear them once again for the audience. Thank you.
Thank you, dear. Dear Gordana, I couldn't listen you exactly because of voice problem. Could you please repeat your comment or question?
Hatice, I just asked you to repeat the conclusions of your presentation.
which was very well elaborated. We understood very well.
Thank you very much.
But it would be good for the audience to hear the conclusions again.
Oh, thank you very much for your good opinions about our work. Yes, we still continue to apply them on commercial greenhouse system, not only for plant pathogens but also for some insect pests as entomopathogenic effects.
Hatice conclusion'ı biraz daha açar mısın dedi ama.
Daha ne kadar yani daha ne kadar açayım bilemedim. If I give more explanation for conclusion, our bacteria are still in registration stage, but there are some official problems for registration in Turkey, like in European Union countries. And I don't know how I could explain, how I could give more explanation.
I understand your problem very, very well, because we are not European Union, but
yes.
So in our country we have a very complicated procedure for the biostimulant, biopesticides, all the plant protection products which have prefix bio are very, very complicated to be registered.
Yes.
Instead of supporting this kind of plant protection products, instead of promoting them in a way, we make their use a little bit restricted and complicated.
Yes.
Thank you, Professor Hatice. Professor Gozen Dumicic, I assume that you are here on behalf of Marin Sukrov?
Yes, hello for everyone. I have technical problems in the start, so I try to turn on my camera, and I success that, and now I could talk with all of you.
Well, that presentation is very, very interesting.
Yes.
But it was so good and fluent in English that we could not catch all the flow of the presentation. Could you please repeat eventually the conclusions of the presentation for the audience?
Okay, so we conclude that the rootstock has the higher influence on for the tolerance to root knot nematodes than the biostimulants, because with you know that with biostimulants always you have some problem, because if you establish some experiment, you don't get same result like producer declared on declaration, and the reason usually is the time between the products made and used, or the storage of products. If his condition is not very well, then the biostimulants lose some effects at plant. And in this experiment, the candlename was a better biostimulants with combination with rootstock Arnold. But 1 year ago, we repeat the experiment, and then we had some difference. So the Intera had a better result than candlename. So we could not conclude strictly that that some biostimulants it's much better than other, or that some rootstock better than other, because depend about soil, about technique of growth, about climate condition. So I think so that all rootstocks is very good, for the tolerance to root knot nematodes, and biostimulants could help to avoid the attack of root knot nematode. Sometimes sometimes some rootstock or some biostimulants be better.
I also have some question for you.
Okay.
If it's can I ask?
Yes.
Okay. Have you ever tried to apply biostimulants in a period, like, for example, to apply this week, and after 1 week you apply again some?
Yes, we applied.
Do you have any differences?
We applied 3 times every 15 days when we start applied. So when you the producer told us that when you start to apply the biostimulants, you have to apply it continue every 15 days. So we applied every 15 days the biostimulants.
Okay. And the results are better or not so much different?
The results is better if you apply many times or if you apply just once.
Okay. Yes. Thank you very much. That was the question.
Thank you.
Professor Katja Janic, do you eventually have anything to add? Because you had the poster presentation, maybe there is something you want to comment on it? Will you please unmute your microphone?
I apologize. Good afternoon to everybody, and my huge compliments to organizer. Related to the question, are you requesting about Gvozden's presentation, or I have something to say about another article?
It was not my question, it was more of a comment, because you know, poster presentation may sometimes be in a way restrictive. Maybe you want to add, since you're just with us now, something that was not mentioned in your presentation.
My presentation, where I was the first author, was related to the problem of whitefly resistance, Aleurothes vaporariorum. It is also economic pest in North Macedonia. 10 years ago, I was in greenhouses in the south of your beautiful country. So I would be able to see the problems posed by Trialeurothes and Bemisia. In conclusion,
bigger problem with Tuta absoluta. I assume you have the same.
Yes, we also, colleague Gvozden knows very well. We also have one investigation using tomato rootstocks, and we observed, we have also and numbers. We observed that the rootstock kernel shows the less appearance of Tutas mine on the leaves. But it wasn't complete study on Tutas, so we didn't publish that result. But related to whitefly problems, I can only say that all of us globally have to apply the integrated pest management, because a lot of insecticide caused the resistance in the pest, and we have another problem. Lot of active ingredients we couldn't use in Croatia related to European legislative. So we really must to use natural enemies or other kinds of integrated control.
You know, it was very interesting because regarding your presentation, I can very well expect that grafting might be solution for soil-borne diseases, for nematodes, as it was presented. But it's good to know that there are investigations such as yours to use grafting as a method to fight insects as vectors of various diseases as well.
Yes, we published some articles based on the grafting effects on aerial pests, but primarily whiteflies. And we concluded that grafting can cause modification in leaf anatomy.
Great, great. Thank you very much. Before I conclude this session and the whole day, I have to mention that we had in this plant protection working session two very interesting contributions from Elena Karimova and Evgenia Lozanova, both from the All-Russian Plant Quarantine Center from Pikovo. Unfortunately, they were not able to participate. However, their papers are included in the ACTA, in the printed version, and you can read them, the ones that have not the printed ACTA, you can find them online. And with this, we are finishing the first day of the symposium. Thank you all to all presenters, especially to the chairs that have managed in a relatively efficient way to lead the discussion. And I repeat once again, if there are any additional questions, not only for this session, but for all the working sessions, you can communicate our web page, the Symposium web page, and we will transfer your questions to the respective authors. Have a very good day and see you tomorrow at 10 o'clock.
Thank you very much. And we are sad because we are not in situ in Ohrid.